All right. Good morning, everybody. Welcome to the final day here. I guess for the rest of the meeting, we have 3 talks this morning and 4 after the break is on Jedi. Apologize that I'm up here instead of Dan. We all wish Dan were here. The other thing I'll apologize for, I'll be fussing with my phone at around 9:24 or 5 to check in for my Southwest flight, so I'm not in C40. So no disrespect. Okay. First, Dom Heinzeller is up. Take it away whenever you're ready.
All right. Can you hear me okay? Okay, great. Awesome. So thanks for being here. It's the 3rd day of the workshop, still pretty early, and we're talking about infrastructure. So I understand if that's not what keeps you up at night, you can go back to sleep as long as you wake up halfway through the presentation. We have a little quiz, and then we talk about the key takeaway points. So today's presentation is a bit different than all the other SPACstack presentations I've given so far, because we're talking about research and development, R&D, research to operations, R2O, and operations to research, O2R. And so to set the stage a little bit, there's been an issue in the US weather enterprise, not only limited to US, but anyways, that has to do with transitioning innovations from research to operations, and then back operations to research. And so there is a gap, a disconnect in that feedback loop, R2O to R, that has also been termed as the Valley of Death. And this term has been coined basically by a report of the National Research Council and all the way back until the beginning of the century, where they talk about from research to operations in weather satellites and numerical weather prediction. So often when you hear this term Valley of Death, people think about NOAA and weather forecasting, but that's not true. It's much more than just NOAA, and it's more than just weather forecasting. Either way, the interesting thing is that in order to solve this problem, the various agencies have all come up with some solutions that involve some sort of fancy geometrical shapes. And in the case of NOAA, it's the research and development funnel that you see here. And if you look closely, then you can see that it not only talks about scientific innovations, it also talks about technology transitions. And so just as NOAA here is a space weather R2O to R dashboard, a dartboard, that the CCMC, that's the Coordinated Community Modeling Center hosted at NASA, has come up with, because they were dealing with the same problems. And I've also found mentions of the Valley of Death in climate sciences, where they talk about the 3 E's of climate services: engagement, entrepreneurship, and evaluation, to help bridging that gap. So it's a bigger problem than just weather forecasting, and it involves more people than just NOAA, what we usually think about. So now that we know about that, let's talk about SPACstack. Hands up, who hasn't heard about SPACstack yet? Okay, good. If you hadn't, then I would think you'd lived behind the moon for the last 1.5 years, because I've been basically preaching to the choir every day, and poor Yannick and others who had to suffer through that. But, you know, you got to do what you have to do. Anyway, so SPACstack started more as a garage project between 2 developers, Kyle Gerheiser at NOAA EMC and myself at JCSDA. And it has since evolved into a fully joined effort of JCSDA, NOAA EMC, and EPIC recently. It's a one-stop shop that builds everything that's required JEDI with various Earth system models. And not only that, it does a lot more. And so to highlight that, NOAA has started transitioning its entire unified forecast system suite of applications from their current solution, HPC Stack, to SPACstack. And very exciting also, NASA GMAO and the Naval Research Lab have also recently started exploring SPACstack as an alternative solution to their existing software environments. That's the BaseLibs for NASA and whatever NRL is calling its environments. So if you look at those 2 boxes down there on the left side, you'll see a range of environments and applications that we support out of the box. And no surprise, you see a lot of JEDI plus X, but you also see a lot of UFS applications there. And if you look at the right side, that's just that box basically is all the systems that we support platform. So there are specific HPCs, you have most favorite and least favorite ones will be in there. Then there are generic architectures like Mac OS and Linux, but there are also containers and cloud platforms. Very exciting. End of last week, we moved the SPACstack repository from NOAA EMC to the JCSDA space to highlight that collaborative effort behind it. It sits in the public space. Is that a laser pointer? Well, anyway, it sits in the public space, so JCSDA, not JCSDA internal, and it is fully open development, and it will remain like that. So no worries here. All right. So looking under the hood a little bit, SPACstack is a thin layer that wraps around the open source package manager SPAC that is developed at Lawrence Livermore. And that effort, SPAC itself, is a big thing. It's very well funded. It's got several full-time FTEs only working on that system. And it's got an entire army of users and hundreds of active contributing developers. So that is a community that none of us can replace with our own people. And so what we're doing here is we are building this layer around SPAC to make it a little easier and create an environment where we can build nearly identical software environments, software stacks on a wide range of platforms with only a few commands. And so this is the seamless aspect that I'm talking about all the time when we talk about SPACstack. And so what happens here is that we take our SPACstack that points to a specific fork of SPAC, and we use that for buffering changes that we merge with the authoritative repo back and forth. And then we use a template for an environment that says, I want to build this application. And then either a specific site configuration for an HPC or some generic instructions for building on Mac OS or Linux. And then we can take those and build on AWS. We can build on an HPC. We can build on workstations, laptops. We can use the same set of instructions with a SPAC container feature to build 3 sets of containers where we can build whatever we want, but we are building 3 of them with different compilers and MPI libraries. We built them as Docker, as Singularity containers, and then we host those on the AWS Elastic Container Registry for our own purposes. And the ones that we're allowed to push to the public, can't push Intel because of licensing restrictions, we put on Docker Hub and Scilabs. And so these containers serve a range of purposes. They are serving our automated testing system that I'll be talking about in a bit. People can use them on HPCs in the cloud or workstations if they don't want to or cannot build SPACstack. And of course, they can be used for the tutorials in the academies that came up yesterday. By the way, I can't see the timer anywhere.
You're good. 6 minutes.
Okay. That's nice. Okay, thanks. All right, so it's fine. Yeah, you just kicked me off the stage. All right, so let's talk about the current JEDI automatic testing framework. And I'm saying current here because Evan is going to talk about the next generation that we're currently building. But that's what's happening at the moment. So right now, for every PR or push to a branch that's connected to a PR, GitHub webhooks trigger 3 AWS code build projects. And those use the SPACstack containers that I just described in the slide before. Those builds are successful. They launch a suite of tests, and then the results are uploaded to CDASH. And very likely you've seen all this in your work with us. On the right, behind the scenes, there's an entire machinery of Amazon Web Services, tools, and utilities that make all this happen. There are also nightly builds on selected HPCs and on AWS that run, and they are also using SPACstack either in form of the containers or because it's built directly on that platform. And in addition to the build results, they have for significant changes in runtimes. We have to look at it more than we do now, but they do, and also code coverage using CodeCov. Why I'm mentioning this here is we usually think about this in the context of making it easier for developers to see if their code changes are correct, for the reviewers so that they can focus on the scientific innovation in pull requests, not on the missing semicolon at the end of the line. But there is also another side to it. It also serves the infrastructure team to vet and get more confidence in the software stack, because if all this machinery works every day and every time, we bring in a new software stack, build against the known version of the code, and it's all still good, then we have some confidence that the software environment that we created is working okay, especially because we do this across different compilers, containers, HPCs, and so on and so forth. All right, now it's time for a little fill in the blank with Dom. I'm going to test your knowledge if you paid attention yesterday. We talk about JEDI Skylab. So the Skylab Earth System Data Assimilation application combines JEDI with close. You got to be kidding me. Eric, help me out here. All right. Well, I'm going to have my, well, I had my 2 snacks here. What do you, with the research repository for data and diagnostics, R2D2, and the experiments workflow orchestration kit, eWork. Okay. No one can claim those. Anyways, you failed the test. But he had some good suggestions. Anyways, for nightly testing, research, development, and soon production. The point I'm making here is that Skylab uses Backstack for all its dependencies underneath. And because Skylab runs on HPCs, user laptops, and workstations, and on my cloud, we get the same 2 benefits that we have for the CI testing. It gives confidence in developing the product, but it also gives confidence in vetting the software stack that we are creating newly every 3 months, basically. All right, so this is the important slide that I would like you to take home. And as I said, forget about everything else. This is the important one. So my point here is that because we have Backstack, we are enabling research and development, research to operations, and operations to research. And I have come up with a hypothetical scenario here for the example of NOAA. That's not some sort of preference. It's just that I know the organization NOAA better than the others, and they are furthest down this Backstack road. So in this hypothetical scenario, you can tell right away it's hypothetical because it starts with me making actual meaningful scientific contributions to JEDI, which hasn't happened yet. But anyway, in this scenario, I'm doing this on my own macOS laptop. And Anna is then picking up my code and solving all the problems that I've introduced. And she might be doing this on Hercules. If we had stayed with the previous solutions that we had in place, you have to look at the side scripts because there are some grayish sort of text underneath the other one. If we had stayed with the previous solution, we would have done that with JEDI Stack. And JEDI Stack had some small issues here and there. Granted, if we had put all our Backstack development efforts into JEDI Stack, we would have solved those easily and it would all be fine. But it would not get us across that valley of death because when Anna gives that code to Corey at EMC, who needs to vet that for operational implementation, he needs to go to a platform that is closest to operations, which is Acon. Well, the problem here is Acon doesn't have JEDI Stack. Acon has HPC Stack because that's what NOAA EMC was using in the past. And so suddenly you're introducing a whole new degree of freedom, or many of them, in addition to the problems you already have with different compilers, different machines, whatever else it is, because are you using exactly the same version of a library? Are you compiling it exactly in the same way? Do you use the same compiler flags, the same options, and things like that? So many things can go wrong that add to the problems that you already have by going from one machine to another. And then Corey gives all this. Once he solves all this, he takes Anna's much improved JEDI UFS, turns it into the awesome JEDI UFS, and gives it to GDIT, who then puts it on WCOS2. Well, WCOS2, if it had HPC Stack, would be using some way of HPC Stack. It's not exactly the same. I don't understand the process very well. It had to do with packaging up everything by EMC, putting it in tallballs, and then rolling it out on WCOS. That's the famous vertical structure that people often refer to. Yet another, possible source of, obstacles and problems that come in. So we want to avoid this, obviously. And so the idea is here we want to have something that supports this funnel from research to operations, all the way from the basic research to the operational implementation, with all these different gates in between where innovations are filtered out. And my point here is that you can do that with Backstack, because in our current environment, we've gotten to this place now with EMC. I'm using Backstack on my macOS. Anna is using exactly the same version of Backstack that guarantees you it's built in exactly the same way on Hercules. And that version was built by Epic. And so if there is a problem, there is support from Epic people. I don't have to support every single platform that we are working on. Anna then gives that to Corey. Corey is working on Acon. Well, guess what? There is Backstack. It was built by NOAA EMC. And so there is support from EMC people. And then it goes to WCOS2. And guess what? GDIT has decided to use Backstack, or maybe just our Stack fork without that convenience layer around it, but the same version of the software stack. And they would be given the full recipe from EMC how to build that. So you have guarantee that you have the same environment with the same options and everything being done the same way. And that is why I think that Backstack enables research and development R2O and O2R. All right. Scientists, you can go back to sleep. This was the most important thing. I'm going to talk about a few challenges and next steps. And the first one is around leveraging automation for installing, testing, and deploying entire environment in hours, maybe even minutes, but certainly not in days in manual labor. So the first part of it is the comprehensive CI testing pipeline that I mentioned beforehand that goes all the way from the software stack to Skylab. So the goal being that changes in an upstream repository trigger a full set of tests. We store the build artifacts to make all this faster, and then we run integration tests on the cloud or on HPCs. And then all those related code changes are tested together and merged together if they pass. So the goal is not to break JEDI. The second one is we need to automate the builds of SPACstack, and we want to share the work implementing these automated builds on HPCs and in the cloud, because we maintain all of these many platforms, and doing this manually is just really, really cumbersome. So we haven't decided yet what kind of solution we're going to adopt. Maybe something that NASA is doing in terms of secured self-hosted GitHub runners. Epic, for their part, have decided to use Jenkins and then put this on all the systems that they support. All right. We also want to enable data assimilation, research and development in the cloud and make releases a community effort. So JEDI Skylab at the moment runs on AWS EC2, whether that's single node or a parallel cluster environment, kind of an HPC environment in the cloud. Our goal is to port this to Microsoft Azure and Google Cloud Platform, and also Noah Parallel Works. If you're not familiar with that, Parallel Works is sort of a Terraform-based system that is cloud provider agnostic, where you have one entry point, and then from there you can go to AWS, Azure, or Google. And we are going to use this as our sort of entry into these other platforms. And then, of course, we need to test and optimize on the operational systems like WCOS2 for operational implementation. We also need to add full support for Neptune and GEOS and SPACstack. It came up several times this week. So I have all those required third-party dependencies in the software stack. And then very important, have NRL and GMAO configure additional systems. We don't want to support all those systems ourselves. We want to share this work with you. So Sarah is hopefully, going to manage 2 or so of those 6, whatever HPCs that you're working with, and then GMAO will configure those systems that we are not typically working on, but using the same software environment. And then the long-term version really is make JEDI installable via SPAC so that people from the community can go to the authoritative SPAC repository and can do things like SPAC install JEDI Skylab version 3.1.0, disable the UFS component, enable GEOS. And that is all that I have. And unless I have another minute, so let's do that. I just wanted to show you on this bonus slide how easy it is to build complex environments. So here's a handful of commands that you have to run. You need to load a few modules that are available outside of SPACstack. They are fully documented. It's all version controlled in our repositories. Then you clone the repository. You run a bunch of commands to create an environment. Everything that is blue on the slide is the extension that we wrote around SPAC. That's the SPACstack extension. Everything that is black is native commands. Then you need to enable and disable compilers in that environment that you just created. That will soon be a SPACstack command as well. Then you concretize. This is where SPAC goes and creates the DAG, the directed acyclic graph with all the dependencies and everything resolved. And then you install. That can take a few hours depending on where you built this on. It's getting faster in the future. We are going to what we call binary build caches, where we reuse previously built environments. Then you generate modules. You can do Lua or TCLTK modules. That's all done by SPAC with one command, SPAC module refreshed. And then we create those meta modules that make SPACstack look like JEDI Stack or HPC Stack beforehand. And that's what you get from those few commands. That's a full environment with all modules built by SPACstack on AWS pCluster with those 10 commands. All right. That's it. I'll go back to that slide. Thank you for your time, and I'm happy to take questions.
Yeah, we have time. Very nice. Chris, please. Bill, are you checking online or somebody? Thanks.
I have sort of a philosophical question about an edge case. Suppose there's a university investigator who has access to, a cluster of some kind that you've never seen before, and they want to run on that cluster. Is your recommendation that they work with you to figure out how to install all this stuff through SPAC? or how would you approach that?
So it depends a little bit on how close they work with us. We have one case that's the University of San Diego, Caroline. She is working with us at JCSDA. Ben Rustin has connections with her. And she is having this cluster called Comet, where she's building on. Because we are supporting her work a little bit, there's a bit of back and forth. She's one of those people that we add to our Stack channels, like our Slack channel, and she has access. And she's also part of our weekly meetings, and so we'll help her a little bit here and there. But if there is a build problem with a specific package, we send her to Spec directly because, there's this huge community, thousands of people. They can answer those questions much better than we can. So it's a bit of a give and take. If some random other person is coming along and say, hey, we want to use this, then we'll say, here's the generic instructions. If you find problems with it, report an issue. And then we have to decide whether this is a Spec Stack issue that we have to address or whether it's a Spec issue itself. And then, of course, it needs to go to Spec.
Has anybody explored that unguided avenue yet?
In a sense, yes, because everyone in this room who is building Spec Stack on their own laptops are doing that. They're going through the generic set of instructions to create their own site configuration, and then they build the software environment there.
I have a second edge case unless there are a bunch of other questions.
Well, let me just ask if we really don't have a lot of time. I'm going to hold here in the room for a moment. Phil, do we have anything online? I just don't want to leave these people hanging. Is your question kind of quick? Okay.
Like on HPC, you support Intel and GNU. Have you compared the performance of those two compilers?
Well, Intel is always faster, for sure.
Another probably quick one. How do you handle the different versions of the Intel?
So we have a whole range of versions because different HPCs have different versions. We try to use something as recent as possible. But, in some cases you can't. So we support basically everything between Intel 18 and the latest 2022 point, whatever.
Okay, thanks. Good, quick questions, good, quick answers. Thanks, Dom. See, and everybody was actually very interested. Nobody went to sleep.
That's good.
Okay. Thanks,
all right.
Dom. Great.
And nobody got to.
Okay, next up, leveraging cloud computing and Jedi infrastructure. Ashley, Griffin, Evan Parker. This is going to be a bit of a tag team, starting with whomever. Oh, sorry, that's my obnoxious check-in sign. Let me first get your clock going. Whenever is your talk up? Okay, you guys ready to roll?
I'm ready to roll. I'm just run a stopwatch. So I go. Okay. Yeah. Hi everybody. Yeah, I'm Evan Parker. As I mentioned, myself and Ashley will be presenting the infrastructure teams. Some of the infrastructure teams work with cloud computing. Just as a little bit of an outline, the areas of work that we're going to discuss include, I'd say, immediate feature and model development. So this is developer activity working with code and the CI and pre-submit pipeline that we're developing to support that. So this is all about fast feedback and just automated testing for code correctness. We're also talking about feature and model validation. So this is happening on the AWS Parallel cluster, which is I'd say, a HPC alternative platform with many of the same features that runs on AWS. And this is being set up for many JCSDA internal users. And obviously, these practices could be adopted by anyone else who's wishing to use this infrastructure for that purpose. And then finally, we're going to talk a little bit or Ashley for sure is going to talk a little bit about our data validation system, which is, I think, also called the near real-time system. It's also running on AWS on the Parallel cluster, and it's basically running the latest Skylab release with Jedi dev code, as well as real data or similar to real data. So starting off with our automated testing framework, this is what I've been working on for the last 3 months. Or maybe, I guess less than, I haven't even been here 3 months, but since I've been here. But I'm going to slow down on this slide just a little bit since I feel like this is one of the more important ones. We're covering unit testing, which of course is just smaller units of code within a package, testing that a specific package is working and a specific new or existing code block is working as expected. Integration testing generally tests across a single package or groups of packages with some upstream and downstream dependencies. But again, this is testing synthetic code, it's testing synthetic data and individual functions in an integrated manner. And then finally, there's functional tests. This is something that we are intending to be supporting in the future. Right now, this isn't our first goal, but this is end-to-end function using, I'd say, real-ish simulated data and models, actually trying to run the platform end-to-end in a way that models what people actually want to do. As far as, I think I'm going to take an aside here and mention, I think a lot of people say CI, CD, code testing, and really there's kind of three areas of testing that people care about. Sorry, this isn't even on the slide, but there's pre-submit testing, which is what happens when you have code that's on a pull request and it is being validated by an automated system, and you get to see whether or not it passes before you're even allowed to submit. Continuous integration, this is testing code that is already submitted, and it's basically monitoring for correctness the code that it exists in the tip of the develop branch. I went backwards. And then finally, there's continuous deployment, which it gets a little bit fuzzy because we don't actually run an operational system, but we can have continuous deployment-esque systems where basically we're actually pushing to a live environment. Initially, we're going to be supporting continuous integration and pre-submit testing, and continuous deployment is something that I think we'll look at more in the future. But going back more to the constraints, we want minimal configuration. We want to be able to onboard new repositories and new use cases really fast, really easy. Basically, if you write the test, it should work. You shouldn't have to be configuring these things. The build system has to closely model what's being used in real systems. So that's in our development system, in production systems, on the clusters. This is easy nowadays because basically that means use Backstack in the most common way. Don't have some custom build system that's in any way different. This has been supported with some level. Some repositories support this well. Other repositories have sort of, I'd say, custom build systems. And the goal of this is to say, no, we're all going to use one, and it's all going to look exactly like the real world use case. Finally, this has to support internal developers, in-kinds, and external contributors. So that means at least there's some thought to security. We don't want arbitrary code running against secure environments with infinite capacity. Anyone who's worked with AWS Cloud at all, and if you haven't, you'll be prepared when you interact with it. It's a giant Swiss Army knife, right? There's over 200 services. Many of these services have first-class interactions with other services. So the combination here is honestly, I don't know if anyone's, I'm sure Amazon has quantified it, but I couldn't find any numbers. It's huge. And just knowing what to do is never exactly obvious. We looked at a few things during the design phase of this, which was done during AWS ProServe contract. Really, it can be grouped into two types of systems we looked at. One is integrating with GitHub Actions directly. So that's basically letting GitHub and their first-class action running system sort of run the show with AWS as sort of a metal allocator for GitHub. And the other was that there were two different AWS first approaches we looked at. As far as what we chose, a little bit that has to do with our capacity planning. GitHub Actions have a preference for reserve capacity. You need to set the computer up. You need to set your remote VM or other execution system up to receive work for GitHub Actions. There are, I'd say, more complex ways around this, but we didn't really go into that level of depth because we want to use the systems as they're intended to be used and not sort of stick things together that weren't meant to be stuck together. In our use case, because we have so many repositories and the traffic is so spiky, right? In the middle of the day, we expect a lot of developer contributions. At night, really none. Sometimes repositories are very busy while other repositories are sitting idle. It really made sense to have a demand-based capacity system, which definitely lined up with what AWS offered. Looking at AWS Batch, which is, I'd say, a generic end-to-end pipeline running system versus code pipeline, We opted for Code Pipeline simply because the concepts in Code Pipeline closely matched what we already wanted to do. So we figured we'd get a lot more bundled, whereas with Batch, we'd have to write absolutely everything from scratch. I'm running low on time because I need to give her time. So I'm going to rush through this and say we ended up doing this with AWS Code Pipeline. It's being initiated by a AWS Lambda function running off of a GitHub webhook. I have a whole design document on this. I feel like this is actually the less interesting part, but if you would like it, you can contact me by email and I'm happy to share it. And then, yeah, basically this is the look at the pipeline. We also have a caching system where we're storing built binary artifacts on S3. This is trading, a couple $1,000 or more of compute time for just a few $100 of storage. Because a lot of the built artifacts are being reused over and over, so long as that individual repository isn't advancing forward in version. So I'll let Ashley take it from here. For the
So you guys know you're in good shape.
yeah.
Do you want to go over more?
Oh, wait, we have 20 minutes.
Yeah.
Yeah.
Okay. Can you guys hear me okay? Cool. So as Evan mentioned, he's doing stuff that allows us to move forward with our development in a confident manner, as well as science. So we're going to go forward with a little bit more on the AWS Parallel Cluster, and we're setting that up as a research and development system. So we have a lot of key benefits here, and I have a list that I'll go through. We're able to add individual accounts for the JCSDA core members, as well as in-kind members. This gives users the ability to set up their own Jedi Skylab. They can develop with that on our AWS platform. This also includes a pre-built SPAC stack setup, and this will be on our shared file system. So, say Dom sets up SPAC stack on AWS, we'll all be able to access that version, as well as probably develop versions and other releases. We can also run the most recent developed branches with Jedi Skylab, and it's relatively cheap. This also gives us the full control of the system, so we don't have to wait for system administrators to go ahead and push an update that we need or an OS, during a maintenance window. We'll have the ability to control that and do it ourselves. Along with that, it makes it very agile. So say we need that OS update. Well, we can push it when we want, but we can do it on a whole different cluster. If it works, then we'll keep it and we could push that out to the research and development system. If it doesn't, we'll just roll it back or just drop it entirely, since we already have an instance stood up. The AWS Parallel Cluster also supports multiple instance types. It does cluster management, resource scaling, job submission queues, job schedulers, such as AWS Batch, which Evan mentioned, Slurm, as well as they have a lot of documentation, tutorials, and support. This figure down here is just from Amazon, and it kind of shows some of those highlights that we're talking about. So moving forward, we're looking to set up a near real-time system as well as that research and development system. For this system, we're hoping to have the flexibility of the latest release of SPAC stack as well as Jedi Skylab, or we could run that latest development code. We're hoping to run operational resolution, and we could run this on cloud HPC such as AWS Parallel Cluster or other HPC environments. So the example of AWS Parallel Cluster that is really nice for us is you can easily add data streams that are already available on the S3 buckets, which is Amazon Web Services simple storage service. This image on the right shows the registry of open data that's already on AWS, and they have a handful of different climate data that we can access. And that's pretty easy. They have AWS S3 Explorer, so you can go in and see what data is actually there. This is just a snippet from GPS, so reanalysis data. Unfortunately, this one in particular only goes to 2020, so we can use it for archive data, but we won't be able to use it for the near real-time system as we're pulling in data live. But that's just kind of one of the benefits of moving towards this parallel cluster as we set up a near real-time system. So going into this near real-time system, current work is being done. A lot of it's by me, Yannick, as well as our observation teams with Ben and Sam coming on board. And so this near real-time is starting with an observation ingest suite. This is going to leverage our existing EWOC package, and it'll set up an ingest workflow for observations. The key components of this is having a fetch, a convert, and a store tasks that'll run through for various observations that we're going to be pulling in. So for the fetch, we're looking to grab various data sources from methods that are driven by a YAML configuration file. As you know, we have obs coming in from various locations. It might be on FTP. It could be on an S3 bucket, stuff like that. So it's a little hard to get what we want. All of it's formatted differently. It has different timestamps. So we're looking to set this up in a way where we could, seamlessly add new sensors or new data that's reusable by us and other people. So that's kind of the fetch point. Then we're going to move into convert. So the goal is to convert all of these different data formats into a unified format, being YODA format. This can be done using existing YODA converters as well as other converters that are used by our observation teams. And then we'll go ahead and store it into R2D2. This can be on AWS or other HPC infrastructure. So this image on the right is what I have right now as a draft. So this isn't available yet, but kind of shows you the work moving forward and how it uses the EWOC workflow. So for this, I just created an experiment, if you will, using the same create experiment that you learned about yesterday with JEDI Skylab. You can see it has this 6-character experiment ID with it. And then underneath you have this new ingest point where it has different tasks. Right now I have fetch and convert in there, but we're still working on store and other processes. But it flows really well. It's easy to see. You can see it ingesting at 5:15, 2023. This is cycle 1. I think I did this for 3 cycles or so. And so again, it's very similar to EWOC where it pulls in the data each cycle. It'll fetch it, convert it, and then eventually store it in R2D2 so we can use it for experiments. And then down below is just kind of, I guess, proof of concept, but this is just GDOS data that's actually converted to YODA format. So we're ready to go ahead and push that forward. So the big picture of this near real-time system is being able to run and publish Skylab experiments with near real-time data. We're going to have the ability to integrate new data streams into forecast products within days. I kind of tried to visualize this on the right where we have, our ingest suite with the fetch, convert, and store. But when we have a new sensor coming in, hopefully we only have to add a new YAML file that can be called during this process, and we're good to go from there. Of course, if it has a different way to fetch data, we might have to add a little bit more development into our code base, but it should be pretty easy to add upon as the goal. We're looking to expand to other cloud HPC platforms. You can also, I'm running this right now just on my Mac with little, just a little bit of data, not too much. It's very portable. You can also, we're looking to leverage other workflow engines such as Silk and other emerging technologies. Right now it does use EasyFlow, but it's written in Python, so it should be really easy to uplift and convert to Silk and what else comes. So, yeah, that's it for now.
Anything online?
So I have a question about the pre-submit tests.
Yeah.
So one of the tests is code coverage, and that relies on CodeCov, which I'm under the understanding that it requires licenses and there's limited licenses. So I was wondering if there was any plans on making code coverage testing more or less opaque to people who don't have licenses.
Yeah, I'd say that isn't in our. I'd say that isn't in our current scope. Yes, that is. I'd say important infrastructure, and we're going to have to look into that after we get out the initial, unit and integration testing. But so far we haven't gone into that.
I think this one's more toward Ashley. So I'm a big fan of PubSub data models. In particular, LDM has been used here, invented here. It's been used for many, many years. I've used it for 30 of those years, and it's got the advantage of no fetch timer, if you will. So it can be basically continuously pulling in the data. So a lot of data does dribble in, and it would be better if it was just converted on the fly rather than aggregating it and converting it in bulk, which can sometimes be very slow depending on the type of data.
Yep.
So is there any plan for that to work as is? Because as far as I know, you can't just say pipe this converter in a real-time stream. I'm looking for Steve Bourbon.
He's right behind you.
For just the addition of live stream data to just continually fill a YODA file of NetCDF. I don't even know if that's possible, but I know it's one converter is one way, but I just like add, append. Open question.
Wanted to respond to that. So there are plans this year to do some upgrades in the ops space. And one of those pieces of that, I think, is to add an append function. So we can do what you're talking about, with the idea that maybe you can pull in knobs as a run is in progress and then attach those to the knobs and then assimilate them. So there is plans for that.
Yeah, and just to know, the good thing about LDM, you can also run it on Amazon. You could use it in a Docker container as well. So that's definitely something that we have on our radar to do.
Eric, let me hold you 1 second. Anything? I just want to give folks online a shot. Okay, shoot.
Yes, in reference to the near real-time system, when this thing gets pulled up and is in full-time production, about how many different observational sources do you think you'll be ingesting, and how many of those will require conversion? How many different formats are we dealing?
So it's probably a question for Ben on how much of those obs need to be formatted and converted. So I'm not sure, but I'm trying to write in a way where you could, if you have observations on RDA already, we can spin up this ingest suite with those observations there, as well as put it in parallel with some that are coming in.
Ben, just give me a number.
5.
Done. No, quick, please.
But we can talk offline. I mean, the idea for the real-time system at this point is really get a lot of the main, and we'll probably use a lot of the nomads type 6-hour DOMs. We get a lot of the main obs types, but we really just want a demonstrator. So when a new type comes in, those will be the ones where we'll maybe have to deal with new formats, because we'll be dealing with a brand new emerging technology. It won't be through an NCO pipeline or anything yet. These will likely be in whatever the CalVal team gives us. So a lot of those are NetCDF that are HDF5.
Thanks.
Yep. Thank you.
So last talking for the break is Ricardo. We'll be talking about the GMAO approach to getting the background error. A33.
Good morning. So I'm now going to put the technical people to sleep, and hopefully the science people will be awake, but I can guarantee you that. Let's see if I can operate this in some reasonable fashion. Yes. Okay. So I will talk about, and some of you have obviously heard about this before, the bringing the GSI background error covariance capability to JEDI. So this is the status update, and the people who have contributed quite a lot to this are listed at the bottom here. So let me just give you a view. And this is, in my mind here, is a work. Well, this doesn't work. Yeah, so it's a work in progress shop for me. Okay, so it's really, I'm going to show you something that doesn't work. So yeah, it's part of the game. Like this too here, too fast. Okay, there's that delay. I'm actually affected by that delay. Okay. All right, patience is not something I have. So the initial implementation is aimed, so the thought of this is sort of this thing about trying to minimize the amount of work in some sense. So though it is a lot of work, no matter what, that we have to go through in order to sort of change from what we presently have in GEOS, but also for GFS and others, and sort of have sort of a less abrupt transition. So the idea is that we run a hybrid 4D and VAR. So in this respect, we would like to be able to exercise a covariance that we don't have to retune. And so although JEDI obviously provides now the capability through Sabre, to give you a climatological type covariance. And there's also the spectral component that I forgot to mention here that's being added by the Met Office. So those are, things that will give you different ways to do balance. But you'd have to tune from scratch, and we prefer not to do this at this first initial phase of the plan. So what we have done is that we have worked to enable Sabre to take the GSI components in, and then have JEDI have that as an option. So it's all work in progress, and just know that I'm not at this stage anyway, and I don't think I will ever expect these to be identical results or to give identical results to GSI. They're just going to give me something that's sort of close enough, and there's plenty of reasons for why things are not going to be identical. So this is sort of a broad brush schematic. Ron showed that something like this in the first, a little simpler version, more understandable perhaps version of our workflow. This is the workflow of the deterministic DAS for GEOS. And, at the heart of that flow, there's a little box there for the GSI analysis. And essentially what we want to do is to enable this flow to also run, not to just wipe out the GSI analysis at this point, but to run alternatively the JEDI analysis. So what we have is an expanded version of this flow where we just added the green boxes are all sort of JEDI components, if you wish, YODA, JEDI analysis itself, the converters, the YODA converters. And so, and the key thing is, and this is already sort of in place. So the key thing is that we have at some point, and that's highlighted by this red box, by this red sort of open box. At some point we make a decision. There is a little one switch somewhere that says you want to use the JEDI analysis or the GSI analysis to feed back to the model and then cycle with that. So that enables us to either turn off the GSI analysis for good, or turn off or not exercise the JEDI, which you already do, obviously, so that's an easy one. Or just do both of them at the same time and on the fly decide which one to use so that we can actually compare. So that gives us the ability to, for example, even if only one of them is used for cycle, to forecast on the fly from both of them. And then we can sort of, if they're close enough, we should be able to have a decent, comparison. And, FSOI is the same thing. We can do FSOI on the fly for both of them. So that's highlighting the little green box at the bottom. So to do that, obviously, we, as I said, we want to have this capability, the background error capability from GSI to Sabre. So we added a component there. The original interface was Dan who put it in there, and then I sort of filled in the gaps, if you wish. And this is done through the center block, so it's really just there isn't anything in the general other blocks, but just the center block controls the GSI background error because it's a full symmetric matrix at that point. At some point, actually, it'd be interesting to explore the square root version of the GSI B that exists, but that is a maybe, and who knows. So, but this list here, just for curiosity, for those who may wonder or who don't remember the actual control variables that GSI handles, and so that's kind of an important part of the piece of the puzzle. So what we did then is I took a minimalistic approach. So obviously this is the ugliest possible ripoff of GSI that has been done throughout the entire thing, and parts of me are ashamed of that, but it's part of the game that we're playing. And so, although the code looks a lot like GSI in many ways, at least the components that were brought in, none of the observation parts in GSI were brought into this. Obviously, they don't matter. So there is no, for those who are familiar with GSI, there's no setup routines, there are no step routines, there are no int routines. So none of that stuff is there because it doesn't matter for B. And I also deactivated the original capabilities because the original capabilities in GSI, and I apologize to whoever is involved in that here, is a mess. So it really, there's dependencies on morph, and so we don't want to bring that in. Somebody at some point wants to do that. That's another story. But so the code looks like the original code, but if you look close enough, it's not quite. So anyway, so we are able to build this library and have it working standalone. And then eventually, we will show that, okay, it gives results that are reasonable for direct type tasks. And then we put it in the framework of Sabre for Rio and therefore enable it in the FV3 JEDI. There were some little pieces that we needed to change in the control to analysis of the FV3 piece. And then there's a whole bunch of VMOs to test different configurations. So I've tried to do as systematic a test as I can with this. So I've played these games of direct function testing, which I'm almost over with, if not completely over with. And then, having only surface pressure observations or temperature observations or just radius observations or ozone observations. So played all these games running 3D VARC, which is the sort of easiest piece. Then I added the microwave, and there was some, each one of these things, a different mystery pops or a different little thing pops, and then you have to go and massage things or, make sure that GSI is doing what it's supposed to do, because obviously it's a ripped code. And so there's one example, good example is the skin temperature that I at first said, I know this is going to be an issue, and I just bypassed that from the get-go. And eventually I tried to trigger it, and it stumbled on all kinds of issues. So anyway, so it's working now to the extent that I can tell. And then, obviously we got to the point of saying, let's trigger now the 3D NVAR and 4D NVAR and redo all of these. So we go back to step 1, 2, 3, blah, blah, for all these. So it's a little bit tedious, but it works. So what you're going to be seeing now is just these bunch of little tests. And we're going to be comparing increments. So all these figures essentially have the GSI increments on the top. I can't use this. The GSI increments are on the top. And so in this particular case, these are radiosonde observations. So surface pressure, temperature, winds, and Q as well. And so you're looking at the temperature increment, and you have the GSI increments on the top and the JEDI corresponding increment at the bottom with the sort of the background error from GSI. And so things are sort of in the 500 millibar height, and sometimes these plots have a scaling. That's why I have like a GSI equals 1 and JEDI equals 1. In this case, in the very top there. In these cases, I am not scaling the increments, but sometimes just for visualization, because I keep my color scale fixed, for visualizations, I change those numbers and I pop them. So the scale itself doesn't change. The color scale is the same, but the thing has been sort of, highlighted in different ways. So you see temperature and winds that look rather okay. There's some differences, obviously, and I'm not too concerned with the difference because I know the observations are not one-to-one right now. So not everything that goes into one goes into the other. So that gives me some differences. So this is for surface pressure and for ozone, at 20 millibars in the case of ozone. So things are kind of roughly working for 3D VAR. These are sort of the zonal averages of the increments of temperature, U wind, and ozone again. So they kind of resemble each other. So it's again not identical, but close enough for comfort, I suppose. So what I did is, and back then I think I skipped the slide. So let me go back quickly. I think I didn't. Yeah, I didn't actually talk about this corner here, the right corner of the slide. So way back then, before I had this capability to hook up the GSI component in there, the only thing that we could do was just say, for example, do a 4D and VAR type exercise. So what I did is I set up GSI, the GSI system that we have, as a 3D and VAR system, and deactivate a whole bunch of things, which I'm going to go through with you in a minute, and then ran a corresponding JEDI, and then run it for a few days, about 20 days or whatever it was. And then, I looked, for example, at the ratio here. This the first picture on the left corner here is a time series of the JO over N for the JOB or JOA. The solid lines are JOB. And the red curve you can see is the JEDI one. So it's not very good, right? So it's really not quite good. And if you look closely, you quickly spot that the problem is the B. So the bump was not tuned. The scales in bump were not tuned to really provide an adequate one-to-one comparison. So now that I have the 3D, the GSI background error. I redid this experiment. So what I did to just make sure that you understand the fairness of the experimentation here is I have to downgrade, to be fair, I have to downgrade GSI for multiple reasons. So I turned into a 3D VAR, which is not what we use. Obviously, I removed the TLMC. I removed the dry mass constraint. I removed the flow dependency and the background errors. I removed the first gas at the appropriate time. No linear QC, one single auto loop, and 30 iterations. So this is all simplification, a large simplification from what we would do normally. So we still run 3D VAR, as a matter of fact, for real problems. But we don't use exactly this configuration. And so it's a useful configuration. It's a useful exercise to use 3D VAR. So, and I obviously used only these observations, radius zones and the corresponding ozone ones. So what happens now? So I've repeated that figure of the JO over N here on the left, and the new one with the 3D VAR on the right, and I put them in the same scale to just highlight the fact that now with 3D VAR, with the covariances that are fairly, they're sort of near one-to-one, then things behave in a very acceptable way. So I heard here in this thing, which I didn't know, I think Guillaume was the one who first mentioned that Russ and Russ et al. And Guillaume are cycling the 3D VAR, this 3D VAR. So it's not too bad, what they're doing. I know there's some issues, and one of the issues. So this is like time series, other time series of forecast errors that before were very different, and now are much more alike. So I don't have to talk specifically to these curves, but it's here for you to refer to. So there are no differences. Before I had like forecast errors were much smaller in the JEDI system than they were in the GSI system. And that's because the observations are not being listened to. So this is self-verification, therefore you have a smaller error. And so JEDI was showing essentially half of the forecast error than GSI was. So all these things are sort of now this is a different period, so that's why the things are different. So, and these are FSOIs for the two different periods and the two different configurations. Again, the new ones show things that are more reasonable. So let me just then start talking about the problems. So I still have an issue with the moisture variable, and I don't fully understand. I haven't really spent too much time looking at it. Some of it was fixed, has been fixed. Don't need to talk about the details of that, but not everything is fixed. So moisture is still, and GSI has two options for the moisture variable. But neither one of them. The one that we don't use works more reasonably, at least gives me physical looking increments, but it's not the one I use. So I don't really care. And it's not quite one-to-one either. So I have to go back and look at this closely and see what's going on. The other thing is, so what I want to say here. Oh yeah, right. So now the question is that how do we bring in the hybrid capability? So now we have GSI there. So how do we bring this hybrid capability? So again, we have the option to do a bump-based hybrid or a GSI-based. So I brought in the GSI features of hybrid into this because again, we don't want to be tuning bump. And so that's what you'll see here. So let me just show you, and then eventually we'll bring in the TLMC. I'll tell you that in a second. So what we have presently with this GSI connection is all these options working. So you can blend and choose and do whatever you want of all these options, except the 4D ones, which are really the ones we really want, the 4D ones using the GSI ensemble. And let me give a bit of an illustration of what's going on. So just very quickly running through here. So this is just now assimilating only channel 8, which peaks about 166 millibars, channel 8 of MSUA on node 15. Again, the same configuration as before, GSI on top, JEDI at the bottom. And these increments are being multiplied by 4 because now they're much smaller than this. So the scale that's there. So anyways, for visual purposes, I bumped it up. So it's not, so this is in kelvins, right? So you gotta multiply that or divide that by 4. So anyway, so this is a 3D VAR one. It's reasonable to a good extent. So this is a 3D NVAR. So again, the top one is the GSI. The bottom one is a bump-based 3D NVAR. So I tuned only very mildly the scales, but didn't spend too much time. But it's actually, it's reasonable, I suppose, with some exceptions. Then this is the GSI-based one, also has its differences, but you know, it is what it is. And I don't think the observing system is quite one-to-one again, so that's why you kind of see some things that are missing sometimes. And then we go into the 4D. And now this is time zero in the 4D window. So this is a 6-hour window. You have hourly bins, and so hourly snapshots of the background area. And you will see a progression of hourly increments going here. And you can already see the time zero is already odd on the right-hand side. The left-hand side, the bottom plot, is the bump based. The two top plots are the same, they're GSI based, 4D and VAR. And again, I removed the hybrid part. So B is 0, B climate is 0, B climatological is 0. And then we have the GSI correspondent one. And now you look at the simulation. So we're going to simulate first this side, and you can see, the thing propagates in a decent way. Propagates to at the bottom, so that's cool. Now what happens here? So something is wrong then. So it's not quite working. So I think I have right now is a series of a series of 3D UNVARs working for each window, but they're not connecting. And I don't know why that is. So I'm about to sit down with Anna and pray that she actually helps me understand this. But so there's still a puzzle. So it's okay. It's work in progress, as I said. So my closing remarks then are that, the capabilities are there. There's some things that are missing. And I think I'm not going to read all this, but I'm going to say that the next thing in line for this, after sort of these couple of puzzles are resolved, maybe before that, because maybe NCEP will help with some of these puzzles, is to actually bring in the TLMC, which is the balance component and the GSI uses, and that's important, particularly for the ensemble piece. So we want to have that, and that's it.
So did you just say you're not going to pay attention to anybody else's talks the rest of the day because you'll be coding at the chair? Is that what I just heard you say?
Yeah.
Okay, we do have a couple of minutes for questions.
Do you still do analysis in regular Lagrange grid or Gaussian grid?
Yeah. Everything in the GSI, GSI is very bound to its grid, right? And so it's very, very difficult to change that. So everything works that way. But remember, for example, the FV3 connection, the FV3 var.x, the way it connects for us is through a cube. So we actually read the cube backgrounds. And so that transformation happens seamlessly. So I believe that if you were to have MPass fields, that still would happen. It doesn't matter. You still have to worry about, whenever you tune that, wherever you come up with something for that covariance, would have to be on the GSI type grid, but, Gaussian type grid.
Yeah, I know the current GSI already have 4 mechanisms transform back and forth. But my question is that, follow up one is, can we just do the horizontal recursive filter on the 6 faces directly?
Yep. Yeah, it still works. GSI works exactly the same way as it worked. Yeah.
There might be a question for Arlindo. But
sometimes people call me Arlindo, so maybe it will work.
I did that for like 3 years.
Yeah. So with your work, because I talked with Arlindo, it wasn't clear for the update if you wanted to use GSI or BUMP. And with your work, will it lean for aerosol towards using GSI or using BUMP? And in the case they decide to use BUMP, would it be problematic in the workflow in the long term?
Well, I'm going to say this. Arlindo made a choice many, many years ago when we were hooking to GSI and in GEOS and all that. When he developed the AOD analysis, he developed that on the PSAS system, which is the old PSAS. So he did not want to have anything to do with the GSI at that time. Later on, the GSI became a lot more flexible. And I talked to him about explicitly, can we just do this in the GSI, especially because there were already AOD pieces that were brought into GSI. And he basically nicely refused to do it. So I think that they will go along the bump line. That's my gut feeling here.
Oh, that comes the second part of my question. Sorry. Will there be an effort to bring the analysis together between aerosol and methodology? Because that if you make that decision of using JSI on one hand and BURP on the other way, you are like in a situation in the long run where you'll be like separated for very long.
Well, right now we don't actually do the both of them together anyway, right? And so I don't know that we would be doing this but it's true that at some point when you start doing, at some point we are going to do, and we already did this in GSI a long time ago. We did aerosol affected regencies, but we weren't analyzing the aerosol. We were just affecting the regencies with no analysis of the aerosol. So, but we could analyze the aerosol. So. It's one of those things, it's going to be a bit of a...
It's a hard rock to move, to be honest with you, but we'll see.
Yeah.
Sergey or coffee? Sergey or coffee? Okay.
Wow, Ron.
Better be good.
How hard it will be to actually start exercising spectral beam, this FP3 setup that you have right now?
I don't know. It's probably doable because the Met Office has made considerable progress. So, and they have a more general code than the GSI code, right? So I imagine it is doable, but somebody has to work the knobs but yeah, I mean, there's many advantages to do the spectral, right? Particularly when it comes to the balance part. So. But I think that no matter what, the ensemble is always going to suffer from not having balance, and you're always going to want to do something with it. I don't know what the Met Office does. So for us, I think TLMC is still going to end up playing a role.
You plan to bring TLMC?
Yeah.
Okay, well, let's thank all 3 talks, 5 speakers for a great... unless I hear otherwise, we're back at 10:30. Okay, thanks everybody. We're down to the final 4, but I do have an announcement here. Lunch today. It's grab and go. There will be bags. Choose your items and take them with you if you need to leave right away. That's what I read here. Does that sound? I'm not doing anything. I'm just the talking head. Does that sound right? What does that mean? I mean, you can eat here if you want, but if you need to, you can just take your stuff and bolt?
Yeah, I think there's no rush to leave.
There is no, okay, that's kind of what I'm asking. All right, we're not getting booted out of the venue.
Yeah, but if you have to leave, it's just, it's...
Yeah, we won't think you're impolite.
Right.
Yeah, I mean, I still will, but I won't say anything. Okay, so like I said, down to the final 4. Clementine Gass is going to talk about the UFS model in Skylab.
Hello, so my name is Clementine, and I'm going to talk about the effort that has been made and is still in progress to integrate and run the UFS forecast in our Skylab experiments. This is work that is done mainly with Dom Heinzeler on the infrastructure team and me on the Skylab side. So you have seen this slide many times before. The goal is to add in that red circle a way for our colleagues and collaborators to easily run a model that has full physics. For all of our colleagues who work with, for example, HTLM, ADA, physics, they would need a model with those full physics available. And so we're working on adding a proxy app for the UFS model. The current capability in JEDI, I'm going to give it to you right now. We have a UFS bundle that is available in our JCSDA public repository, but most of the repositories inside are private, so you need to be a member of the JCSDA internal organization. We are able to build with JEDI the atmosphere component, the atmosphere aero component, the NG-GODAS, and the fully coupled system using JEDI executables. But we only have test cases right now for the atmosphere and the NG-GODAS applications. We are also able to run the UFS forecast in the EWalk suite, so in Skylab, at both medium resolution and high resolution. Medium is 200 kilometers and high resolution is 25 kilometers. And this can run on a laptop, on HPCs, so a select amount of them, and on the Amazon parallel cluster. On the infrastructure side, so the side that Dom mostly worked on, we needed to make some changes in spec stack, adding missing libraries, changing the FMS version, etc. We needed to make changes to the UFS weather model. So we do have a fork of it, but we are trying to keep it close to develop. So we are really trying to stay as close as possible as the UFS weather model as we can, but we do need some changes. We needed changes in the EV3 JEDI interfaces. So there is now a better integrated way to drive the model, initialize all the components that are needed for UFS, including NeoPSI and ESMF, and we can exchange variables between JEDI variables and all the internal variables that UFS needs that we don't know about in JEDI. And that allows us to run, for example, a forecast from a JEDI analysis that does not contain the 200 variables and some that UFS needs to be initialized. On the Skylab side, so that's work that's been done in the algorithm team, it was only needed 4 places in our workflow where we needed changes. So we base the UFS workflow on the GFS workflow, and we needed only to modify the get background, get forecast, save forecast, and get all the static files that are needed for the models. All the other tasks are exactly the same as the ones we would need to run the EV3LM model. We are also able to do on-the-fly changes to model name lists that are needed by UFS. So we can update the forecast length, the forecast output, we can update the time step. And we do have one version of all the static files per release. So right now we have only one, but that makes sure that all the people who are going to be running the model in a set quarter will be using the same version of all those extra files we were talking about yesterday. And on the right here, I put a snippet of the ECFlow workflow if I was to run a UFS model through like a cycled variational experiment. And you can see that really the only differences are get fixed files UFS, get forecast and save forecast UFS. All the rest is exactly the same. Preliminary results we can look at. We were able to run a full month of UFS cycled experiment, which up till now, since we didn't have a model, we were not cycling our experiments. This cycled for a full month. We're using the same observations, our non-cycling Skylab experiment. We're using the C384 resolution for both the outer and the inner loops, and we're using a static B matrix. We're using the 3D var cost function, meaning that the forecast, the UFS model is only run during the forecast step, not the variational step yet. And on the right here, you can see it's just a time series of the analysis of air temperature close to the ground over the whole month. And we can see night transportation. And I also put here an increment of air temperature close to the ground. On the left and on the right, we can see the evolution of the observation cost function throughout the month. We can still see, as I was showing yesterday, the evolution of JO during 6 p.m. and 6 a.m. where it has less observations, and at midday and midnight where it's a bit higher than that. At the bottom of this plot, you can see that it is always using 50 iterations at each cycle, which means we're never hitting the convergence criteria. We're always hitting the maximum number of iterations criteria, which was 50 in this case. The work that is still in progress and the work that we plan on doing in the next releases is update our current Skylab atmosphere land experiment to use the UFS forecast that would allow us to actually cycle our deterministic. And we want to be able to run a 3D FCAT cost function, which comes with a little more hurdle since we do need to rewind the model, and that adds a whole new layer of difficulties. We want to look into using the hybrid B matrix and not just the static B matrix. We need to be able to read external land analysis because JEDI right now is not producing a land analysis. So we do need to ingest those before we run a forecast. We need to merge all of this code back into all of our internal developed branches for our internal repositories so that all the collaborators can use this work and do their work on HTLM, EDA. And we want to set up test cases for both the aerosol UFS and the fully coupled that's going to come later. Yeah, so you should keep an eye out for the next Skylab releases. And I don't know if it's going to be V5 or V6, but there will be a Skylab experiment that's going to be running with the full UFS that you will be able to go on the website and see. And that's it for me.
Yeah, plenty of time for questions.
Very nice talk. This is on.
Try again,
Yeah,
right here.
okay. Very nice talk. So I think that when I see this, what comes to my mind is what's missing to me is the piece that says, okay, you are now, and this is, don't get me wrong, this is great. You're able to cycle the UFS in the framework of the Skylab. But how does it compare with UFS cycled by the NOAA guys somewhere, right? So you don't know that. And I think that's a missing link here because, you know, for as long as they're not running Skylab or using Skylab to run, there's always going to be a disconnect, right? And so there should be, maybe perhaps there is some way to allow for the framework to take in something that's sort of a known. So this is my baseline, comes from, you know, some person who ran this in, I don't know, South America. And then that's my baseline, and that's what I'm going to try to reproduce. And
Yeah, so you are exactly right. We will need to implement more comparison diagnostics. We have access right now to all the 6-hour forecasts produced by EMC because that's what we had been using so far since we were not cycling. This is only a first run of the UFS experiment. We have not tried to even start comparing. So it is coming. Yeah.
Hang on a second, Guillaume. Phil, will you just wave if there is somebody? There is somebody? Okay, just go like this.
And we'll be happy to participate definitely for comparing what we have.
So you can help us with the test case for Ocean?
Yeah, for sure. Yeah. Well, obviously I work with Travis all the time, so no problem. My question is, I'm being a parasite again. I'm really interested in running the UFS in a container in my laptop. So when you said laptop, you can build the UFS. Did you mean you guys have a container that we can use?
It is using SpecStack.
I don't want to use SpecStack. I'm lazier than that. I just want to grab the container that you guys provide and just.
So the container is going to be built with SpecStack. Are you okay with that?
No, well, that's fine as long as. So the question is more: is that container going to be the same one that we currently grab from the? I forgot the Greek.
Use the mic, please.
Sorry, yes. So we'll need to update that container or swap out an FMS version so that we can run the UFS in there. But basically, we can produce one within a few minutes if you want.
Okay. And I say that as a user of SpecStack, it does remove a layer that I just don't want to deal with. I want the container, I want to build stuff in it and go to developing whatever I need to develop.
Yeah, so we do plan on having containers that can run that.
Plenty of time.
I have a question about how when you're cycling, the output from the forecast is getting into JEDI directly, or is it, in core, or is it communicating through files?
So we are actually disabling the forecast output through JEDI. We're only enabling the forecast output through the UFS weather model. And this output is basically the same as JEDI, was just more variables. And this output can be read directly as input for the next variational cycle.
It's read from a file?
Yeah, it's, all the tiles, the different file types.
And then, so my question is, for the S2S, that would also be the philosophy is?
I'm assuming yes, but I'm not knowledgeable about that.
Why do you think it might be different? Yeah.
Well, so like if you want to run 40 var, then this communication by files would not be sufficient. Right. So my question is, in the S2S application, would you be running the full UFS, including CMAPS mediation in core and communicating to JEDI in core?
We haven't thought that far yet.
I'm not saying that is an obvious first step. I'm just asking if that's what you're thinking already, but okay, I understand.
Ideally, we want to move to in-core as much as possible.
But it's
might be steps on the way.
We still have a couple minutes if people wanted to take advantage of it. Oh, Ricardo, you had me going there. Now we all just draw attention to you running to the restroom instead. Okay, thank you, Clement. Very nice. All right, Steve All is going to talk about Vader.
Yes, so I'm Steve Vall. I'm a software engineer here at JCSDA, and I'm going to be talking about Vader, the Variable Derivation Repository. So, quick overview. I've presented on Vader before, but in case anyone know what is Vader, at a very pedantic level, it's a JEDI GitHub repository that contains variable change code. The code that is interesting that's in there provides a framework of model agnostic classes and methods that perform variable changes. So that framework provides a way to modularize an individual variable change, so it's easy for all of us to collaborate, add variable changes to its capabilities, and expand what it's able to do. So generally, if you're familiar with UFO, as UFO is to forward operators, so Vader is to variable changes. And I want to say it's a variable change code refactoring. Sometimes I think people think maybe it's more than it is right now. It's just a magic thing that's going to sit in OOPS or something, and it'll do all your variable changes for you. It is not that yet. It may never be that. And I'll talk a little bit more about that later. So why create Vader? Well, really all the reasons for Vader are all the same reasons for JEDI itself. We're kind of expanding the mission of JEDI into the area of variable changes with Vader. So you've seen this slide before. In terms of lines of code, and the red bars at the top are the model-specific lines of code. Well, before Vader, all the variable change code existed in those red bars. You notice that Vader is not listed at the top of this older slide. So with Vader, we strive to continue to make those red bars thinner, more of the code shared JEDI code. So just quickly, all the benefits that come from this are, again, the benefits of JEDI. A new model coming on will have a thinner model interface to write, allows us to share the responsibility of maintaining this code and improving it, performance or otherwise. It encourages common design, which makes it easier to understand what variable changes are there, how they work. Variable changes right now, there's cases of duplication where the same variable change is implemented in multiple model interfaces, and now we can get rid of that, put it in a common place. And I think it will provide a way to experiment with new techniques, maybe directly. Someone else has implemented a variable change in a different way or a different algorithm for one. And if you want to try it out in your model, it would be very simple if you have Vader implemented to just try that other technique, or indirectly, if there's a process that somebody else has implemented and you need variable changes to get to that process, if they're in Vader, then it makes it easier to access that. So I'm going to talk really quickly about sort of what I feel are the two different high-level aspects of Vader. One is this, what I've been talking about, sort of this library of variable changes that we can build up in the code base. But the other part is the algorithm that Vader has within it that can access those variable changes and solve a particular problem of, given a certain set of inputs and given a certain set of variable changes I have at my disposal, and given certain variables I'm trying to produce, how can I do that? And so there's sort of these two different aspects. There's the library of variable changes, and there's also this algorithm within Vader. So if you've seen any of my previous Vader presentations, you remember nothing about them, but probably this picture. It uses, because I think metaphorically, it uses a recipe cookbook metaphor. Thanks to my son for photoshopping this for me, and giving me at least one memorable slide.
Very wrong about that.
As a Star Wars fan, I had to really limit myself to one Darth Vader picture in this presentation, and this had to be it. This is sort of a diagram of an individual recipe. A recipe is the metaphor I use for an individual variable change. It has a few defining characteristics. Let me see if I can get this pointer to work. That would be a no. Okay, so on the left, it has what I call ingredients. These are the input fields or variables that the algorithm requires to produce a given product variable. So each recipe produces a single product right now. In this case, for example, potential temperature is what I'm depicting with a green hexagon. I'm using colored shapes to represent variables in this presentation to make it more visual. And I'm using this bowl icon in the middle to represent recipes. So at the bottom, the name of this recipe would be called air potential temperature _A. We're just putting a tag on in case there's multiple recipes that produce potential temperature. There's _A, _B. This is the naming standard we came up with. It does sometimes introduce some confusion. People get, so just remember, if you're looking at Vader stuff and you see an _A, _B, that is referring to a recipe, whereas if you see it without that, then you're probably talking about the variable or the field. So what do you do with recipes but put them in a cookbook? And that is true in this metaphor. So if you have a selection of recipes, you put them into a cookbook that is going to be provided to Vader when you create an instance of Vader. And those are the recipes that the Vader algorithm will use when it's trying to solve this problem. So probably the best practice recommended would be to come up with, if you have a particular model, the cookbook that you want to pass to Vader when you instantiate it. Vader does have a default cookbook. If you don't want to mess with that at first, it'll have a default cookbook. It'll work out of the box that way. The downside there is people keep adding things to Vader's default cookbook. It might impact what your code does if that default cookbook changes underneath you. So you may want to control that by specifying the cookbook, but then you do have to maintain as Vader gains abilities. Maybe you want to keep maintaining that cookbook. And if you know that there's a recipe in Vader's repository that you don't want to use, like say air potential temperature _B, you know you don't want that algorithm. You want to make sure Vader never uses that. It's easy enough to just not leave that out of your definition of the Vader cookbook. And then you can be sure that it won't get used. So now I'm going to talk about sort of where Vader sits typically in the code. This is not the only place Vader could be used. Oh, no, I jumped ahead a slide. So this is going to show a representative method call within Vader. So Vader is sitting there. It doesn't do anything until you create an instance of it. So as I talked about, you pass it a cookbook in the constructor, or you allow it to use its default cookbook. And then once you have it instantiated, you can call its methods. So I'm going to be talking about the change var method. It's the nonlinear variable change. It's sort of the easiest to explain at a Lego block level like this. So you're going to pass that method two different things. You're going to use an Atlas field set, which is sort of the generic way we're passing data around Jedi in other areas as well. You're going to pass an Atlas field set that have the input fields that you have to work with. Those are the ingredients. And then you're going to pass it a list of variables that you want it to produce. So now Vader has what it needs for its algorithm to go to work. It's got a cookbook. It's got its list of inputs. It's got its list of what it's trying to produce. It goes through and it produces a list of recipes that it's going to execute in a certain order to produce those output variables. So the return value for that method call is going to be the list of the variables it produced. And it's also, in addition to that return value, it's going to modify the two things that you passed into it. So that field set is going to come out hopefully with more stuff in it than what you passed in. And it's that list of variables needed to be produced is going to come out hopefully smaller than what you passed in, based on what Vader was able to do. You may notice if you're eagle-eyed, there's on the right side of the slide, there's a blue oval that came out of Vader that wasn't either in the inputs or the requested outputs. That's because Vader may create intermediate variables. If its algorithm determines, to produce one of the desired outputs, I need this ingredient. I wasn't given that ingredient, but I have a recipe that can create that ingredient. So it produces an intermediate variable that wasn't requested. Rather than just throw it away, we decided to go ahead and return it in case it's useful to the calling code, and they can throw it away if they don't want it. Okay, so now this is where Vader might fit in to a typical call. This is sort of the use case I had in mind when I designed Vader. It doesn't mean it's the only place Vader can be used, but this is sort of a representative way. So up at the top, I wish the pointer worked. I came up here yesterday during a break and it worked. I had it working. Okay, so I'll remind people up at the top I have an OOPS. So OOPS has a class called variable change. It has a class called linear variable change. These are OOPS interfaces. Those OOPS interface for variable change has a method called change var. So your model already has this implemented probably. And in the before box at the top, that method is provided a list of input fields. It's provided a list of desired variables that might look familiar. And all this blue stuff is model-specific code. So you've already got a model-specific algorithm. It's probably simpler than the Vader algorithm because it has a smaller set of things it has to worry about. It's already got variable changes, and on the left there, it produces the output variables. So what we have done in a couple of models, and what you might want to do if you're one of the models that doesn't have Vader, is you insert Vader into this this OOPS level interface you already have implemented. So you see you've got the same inputs. You might have to massage them a little bit to get them into Atlas field sets to pass into Vader. In this diagram, I've said, let's say the variable changes 1 and 3 have been implemented as recipes within Vader. So Vader is able to do a couple of those variable changes. That green arrow shows is sort of what I showed on the previous slide. It outputs a field set with more stuff in it and says, okay, here's the one that I was not able to do, and it hands that off. And then you still have some blue model specific code to sort of finish off the job to produce the 3 variables that have been requested. So you might look at this and say, oh, well, you know, all you have to do is put variable change 3 in there, and then Vader does everything. And that'd be great. Then maybe you don't even need this OOPS level interface. That would be great. Vader currently has some limitations on what recipes are capable of. They're not insurmountable. But what I want to convey is that that day of not having sort of this 2-stage process could be kind of far in the future. I don't recommend waiting for that. We'll probably have this 2-phase approach for a while. Okay, so if you're a person who never looks at code and you maybe use attention drifted while I was talking about all that lower level stuff, please come back because this is where I need you. I've talked before about Vader. Vader's capabilities have grown. It has 19 recipes, thanks to Dan Holdaway and the Met Office team have been contributing that because Vader has been implemented in the FV3 Jedi interface and the Elfric Light model interface. It's also been implemented in a Vader Saber block so that Vader recipe variable changes can be used within Saber. Some transformations are already there. But we need to continue as a group to build on the framework that Vader is there in order for us to all see the benefits that Vader can provide. I'm just one developer and my time is getting pulled away from Vader. So if you are here representing a model that is not implemented Vader, I hope you can schedule time to do that. I'm happy to help. We came really close during the Vader code sprint in November to getting it into MPass, but didn't quite get there, and then the developer left immediately afterward. So didn't happen. Contribute recipes. If you're working on variable changes, learn the base class, the recipe base class, and what methods, how that variable change has to be structured in order to go into a recipe, and then everybody can use that variable change. One difference between Vader and UFO is that UFO was kind of in Jedi from an early stage. Vader is coming along later in the game. So you probably already have working variable change code, and there are probably higher priorities for you than refactoring that code. So I need you to do it anyway. Because that's how we're going to get Vader to where it needs to be, to where it's a really useful tool for this whole room. And that's my call to arms. And big questions.
You have time for questions?
Talk a little bit about so a lot of times there's redundancy in doing the variable changes, right? Some variables may need the pressure thickness, many transformations will need that. So how do you keep track of the dependencies in Vader? Do you avoid having to redo?
Well, Vader does have a state once it's once you've instantiated an instance of it. If you're using different instances and different parts of the algorithm, again, it comes back to the fact that Vader is a tool that replaces part of the model specific code with generic code. So if you're going to be doing that over and over and you maintain Vader's state, it will remember the algorithm part that figured out, oh, I need these recipes in this order. But other than that, it doesn't really have I guess I'm not exactly sure. It redoes every time it's passed a new set of inputs. It redoes the calculations as it would need to. Maybe we can talk offline.
Just to follow up on that, but if it's in the same call and you need some of those intermediate variables to compute more variables down the line, then this computation, there was like this blue oval that you showed, right? Then if it's within the same call, then it's not going to redo the same computation if it's needed for several variables.
That is correct, yes. Thank you, Anna.
Other questions? I have, oh, no? Okay, sorry. I have one. Can you go back to the previous slide? I mean, so forgive my ignorance, I'm a bit confused. I mean, so fundamentally, this is going to reduce probably substantially what's in the interfaces themselves, right?
That's the hope.
Okay, so, I guess when you say, if you haven't integrated Vader yet, I hope you will, and I'm happy to help. But that means, for let's say FP3 Jedi, you're going to have Vader because all the stuff that originally was in FP3 Jedi is now in Vader. But if you have a model where that's not the case, you're basically not just saying, hey, integrate Vader. You're saying, hey, change your model interface. Like, that's kind of have to rework the model interface, correct?
No, not exactly. So I'll go back to this slide where Vader has been inserted inside this variable change class. As far as the oops at the oops level, the oops algorithms, it doesn't know. It just sees sort of the outsides of these boxes. It sees the inputs and the outputs. It doesn't know that Vader has been inserted there in the middle. So the interfaces stay the same. You will notice that the bottom box is more complex in some ways than the top box, but simpler in other ways because there's less of the model specific code. So yes, you do now have to implement sort of this handoff between the generic Vader code and your model specific code. And your model specific code may require some adaptation to be able to read the information about what Vader was able to do and then do less in response, because the situation is now a little more fluid. But but it doesn't affect the outer lying interfaces. And this has already been done in FV3, FV3 Jedi. So variable changes that were being done in FV3 Jedi are now being done in Vader. Entire files have been deleted from the FV3 Jedi repository because the code that was there is now in Vader.
So those bar charts that you showed of the generic and the specific, those did not yet reflect the reduction in the red because of Vader, right? You're saying?
Correct. That was an older slide that
How much will FV3 Jedi shrink?
I spent a little time trying to math out like how many lines of code had been removed already from FV3 based on the work that Dan did, and it turned out to be beyond my GitHub skills to figure that out. But I can say that there were several files of several hundred lines that were just deleted, were just removed. And there's still, quite a few variable changes that could be put into Vader that haven't been yet.
Okay, that was great. Thanks. So I put us back on time. We were ahead of time. Oh, well. Okay, Eric and Stephen Herbner are going to talk about, I guess, the database stuff, IOTA and R2D2. I guess you guys will be handing off. Yeah. So if the other person doesn't want to stand, they're welcome to sit. It's your call. Okay.
Okay, so Eric and I work on the IOTA and R2D2 systems in Jedi, and we want to talk about how these systems are providing FAIR principles, which is a method of doing data management with large, big data, large data sets. And we'd like, when we've put a bunch of names on here in our acknowledgement, there's a lot of people that have touched on this and helped us out and everything, and I want to proactively apologize if we've left somebody's name off. But the thing that we wanted to point out is that we're getting very good engagement from our partners. We have people from GMAO, the core team, UKMO, and NOAA EMC helping us with these efforts. So it's great, and I would like to encourage, in-kind contributions to continue in that vein. It's really great collaboration. So today we're going to kind of introduce, some of the big data problems or issues that we have in numerical weather prediction, and introduce the concept of these FAIR principles that we would like to follow, and then show how that can help with managing all this data. And then we want to kind of point out how R2D2 and IOTA are providing these principles. So in the numerical weather prediction picture, as a state of the art of that advances, there's actually several factors that are kind of impacting the need to handle more and more amounts of data. One of them is as new instruments come online, and I'm kind of thinking of hyperspectral instruments in this case. Not only are there more and more instruments coming online, but these things contain more and more channels, and it's just an explosion of data that can come from on the observation side in that respect. And I think even in the last couple of months, we've seen announcements of several new satellites being launched into space, and I think that rate of seeing new satellites getting launched is going to just keep increasing. So that's kind of this one factor. Another factor is in the model space, or the model resolution, and as the grid points spacing shrinks, we get an explosion of the number of points that we're trying to save in all the model backgrounds and things like that. So there's another aspect of data explosion there. And then a third factor is the frequency of forecast cycling is starting to increase. So there's more and more places where we want to save states of things. And we saw earlier this week, there were some examples of a global 6-hour cycle, being run in operations, and then a regional 15-minute cycle. And we, as a field in general, kind of pushing towards this mode of continuous DA where new observations can be assimilated as they become available within the same DA run even. And so there's more and more data coming in, and there's more and more states being solved, so that all of these factors contribute to just massive amounts of data. So in the context of the work that we're doing, we wanted to show this picture. It's got kind of a nice depiction of like all these satellite instruments and conventional instruments, I think, might be in there. Yeah, everything's represented in there. And as more and more things come online, it's like this little world that's in the middle that says Jedi is going to keep shrinking down to like a little tiny J, and you're going to have just this swarm of satellite pictures on there. So that's kind of like the volume aspect is growing and growing. And the velocity is kind of the point that I just made on the last slide of more often saving states and things like that as the cycles times decrease. And the variety, of course, there's all sorts of new instruments coming online and things like that. And the veracity is another aspect where we're talking about being able to do quality control and make sure that the data that's going into the assimilation is of good quality. So at this point, I'm going to hand it off to Eric.
Okay, so the first thing I want to do is talk about FAIR principles and how we're implementing those at the JCSDA. So what is FAIR? So FAIR stands for findable, accessible, interoperable, and reusable. So these principles emphasize one main thing: machine actionability, because us as the humans increasingly rely on our computational support to deal with all of this big data that we have coming in as a result of what Steve said, the volume, the complexity, the creation speed of data. And so FAIR principles have been published and advocated for several years now. So let's define what these separate letters mean. So findable. First things first, the metadata and its data should be easy to find for both the humans and the computers. Accessible. Once the user, whether it's the human or the computer, finds the required data, they need to know how it can be accessed. Interoperable. The data needs to integrate with other data, applications, workflows, so that we can accomplish production scale analysis, storage, and processing. And finally, reusable. Metadata and data should be well described so they could be replicated and combined in different settings. All right, so how can FAIR help us? Well, the need to handle massive amounts of data at increasingly shorter time intervals, or cycle times, requires the adoption of a disciplined practice of structured data stores and organized methods of access. The FAIR principles provide these guidelines for us, and they provide metrics for such a practice by emphasizing what matters in the management of large data sets. Now, what I just described as the FAIR principles is at a high level. This is at an abstract level in general of how we could talk about that. But the FAIR principles actually dictate how you do this on a technological level, at the computational level. And so this is a different slide. Okay. Did we skip one?
I think it's one more.
No, is it after that?
Yeah.
Did I?
Yeah, do that.
No. Where was it at? No. I modified a slide this morning, but that's okay. So one thing I want to point out, there's a slide missing here, is that over the past 5 or 6 years, FAIR principles have whole workshops and sessions and presentations and papers that have been presented at EGU, AGU. Lots of technical products are being created, like at the NIH, to handle their data sets. Technical products came out of the NSF, such as the EarthCube program. The Department of Energy uses FAIR principles quite extensively. So let's talk about how we use R2D2 to implement findable, the F in FAIR. So there's 3 basic rules for findable. 1, metadata and data are assigned a globally unique and persistent identifier. Number 2, the data are described with rich metadata. And 3, metadata and data are registered or indexed in a searchable resource. So what we're seeing on the screen in the center is a screenshot of a representation of the different database tables that are inside of R2D2's new MySQL database. R2D2 consists of two different types. The first one is the data type. And here we see we have analysis, bias correction, feedback, and all of our data types are stored in what's called the data registry. The second type of tables within R2D2's server are the indices, such as what data store is this data in? What experiment did it take place in? What host? What model did we use? What's the observation type? And so what we can see, we intercorrelate all of these in order to satisfy findable data with R2D2. So as we can see on the right and in the lower left-hand corner, we have screenshots of actual records from R2D2's database. So the one in the upper left-hand corner is a representation of what an observations metadata actually looks like in the database. So we have an index for observation, globally unique for observations. We have a provider index that's globally unique. So the metadata is described by an index. And then these are associated with other indices related to it. So you take that index and you can, for observation type, and you can see that it's the EASI MEDOC-C. You can take the data store index, the data register index for that observation and determine where you can find that data file. And so here's how we're actually, and all of this is in a searchable, highly optimized searchable resource. And that resource is the MySQL database. So what we're attempting to do is make sure this is also an extendable resource. So right now we have just a handful of tables for data types and indices. But the way that R2D2's front-end Python code is written, it's written in such a way so that all you have to do to add new types are add new data tables. And the code does not have to be refactored in any way. It pulls the schema in at runtime, so it's extendable. Now, how do we talk about accessibility or accessible data with R2D2? R2D2's front end is made out of a very intuitive, simple Python API. And so one note too on this version of R2D2, we started R2D2 again from scratch last October. So R2D2 version 2 is literally only about 9 months old. But so far, we've already got to the point where we're tracking over 5 million data files in 19 data stores on 4 HPCs and 2 AWS regions. And we have a total of 0.5 petabytes. And right now, we're averaging about 200,000 new files a week as people in JCSDA and other partners are running JEDI Skylab forecasts. And so how is accessible defined with FAIR principles? Well, first, metadata and data are retrievable by their identifier using a standardized communications protocol. 2, that protocol is open, free, and universally implementable. And 3, the protocol allows for an authentication or authorization procedure where necessary. So what we're looking at here is examples of how we implement accessibility through our Python API. And we're trying to make this as simple as possible to use. So there's really only 2 classes in R2D2. There's R2D2 data and index, which represent the tables that we saw on the previous slide. And so here we can see we can fetch a data file by giving key value pairs for an exact data file we're looking for. On the far right-hand side, you can see we can retrieve a file just by calling get by index. And so you can say, I want a forecast, but I know it's indexed already. So we can go ahead and get that. And that index is globally unique for all forecasts. We also have other things like get by name. So you can get a provider by name object, or you can get it by index as well. Another thing to point out too is that we had some questions yesterday about how do I find out what observations are in a data store or are accessible through R2D2. We have a robust search method. You give it key value pairs and it will return to you all the information that you need to find out what data files are available and how to access those data files quickly. Now,
okay, so now I want to talk about interoperable data. So one thing to point out is that Yoda is speaking in the context of observational data, not the model data. So we're not talking about backgrounds and analysis files and things like that. It's even kind of debatable if you want to try to make those interoperable or not, because there's all these different individual models that are tied in to the system. So that's kind of like future work and everything. But in the observation data space, Yoda provides interoperable data. And how it does this is to take all these disparate storage implementations that you can put observational data in, which would be the yellow row that's in this diagram, and you present that data to client software through a common, unified, and consistent interface. That's the green row in this diagram. And what this effectively does is encapsulate the storage and hides that from the clients. The clients don't need to know anything about what kind of file or whatever the data arrived in. It just has to know how this green layer works and how the API underneath that, which was supposed to be orange, but it's kind of another yellow color. and that's what the client works with, is that consistent interface. So all the data, no matter where it comes from, looks the same to the clients. So as an example, if you want to write, say, maybe a script or a Python script or an application that plots out data, like what we were showing yesterday in the Skylab demo afterwards, you can have a client application speak to this Yoda API, and it doesn't matter what kind of data you wanted to show, say maybe the raw observations that came in. It doesn't matter what kind of file it came in, you can have that same code deal with everything. So this is the interoperable aspect. And these first three principles of FAIR, the findability, accessibility, and interoperability, go a really long way in being able to reuse the data. It makes it simple for different applications to draw in the data without lots and lots of code development to handle specific cases and things like that. So those three principles get you to data reuse, but another important aspect of this is more of a discipline of naming conventions and unit conventions and things like that about the data, so that you can always expect to see things in a consistent manner. So there's another aspect here where we have developed on the JEDI team observation, or not JEDI team, JCSDA, sorry about that, the naming conventions and unit conventions and things like that for observation and model data. And I'd like to acknowledge the work that Greg Thompson and Steve Ball did to develop these. There's a couple samples here at the bottom of the two aspects here. They put in a lot of work to get this, to work with different centers and come to an agreement on a common naming for variables. And this is another aspect that makes it reusable, is that everybody can kind of speak the same language. They know what kind of units to expect on things and that. So that's that aspect. So hopefully what we've done here is introduce a principle called FAIR that's got pretty wide acceptance in the science community, as our missing slide has demonstrated. But I think Eric did a good job of describing it. There's all these big organizations that have adopted FAIR principles as a way to go. And we have also demonstrated how the R2D2 system and the Yoda system have started to provide these principles and give us access to big data. So the next steps that we have coming here in R2D2, we've got enhanced provenance tracking, developing HTTPS web services for R2D2, and then a nice GUI for kind of running this interface that Eric described. Maybe after I get done with this slide, if Eric's, if I haven't described this correctly, he can add to that. And then in Yoda, right now, we're currently in the first quarter of the AOP 23, and we're working on runtime memory usage improvements for the Yoda reader. We saw this even come up in the earlier days of this workshop, that there are, different centers are experiencing issues, and just wanted to point out that we're working on that. And once the reader improvement work is finished, then we're going to start a more deliberate profiling effort with what we have to see where the holes are, and then go and fix those in a more directed manner. And then in the second quarter, we're working on ObSpace interface improvements, which will start helping more of the access in a general sense, the OpSpace interface is a little bit too restrictive, and it needs to get expanded a little bit to make it more usable in that. So those are the improvements. And I think that concludes the talk, and thank you for your attention. And are there any questions?
We do have time.
Hi, nice presentation, overview. I'm sure that Steve removed your slide so you'd have a little more time to talk. Now, so what I'm having a little bit of, I don't know if you guys have even thought to outputs that the models tend to write out. We call diagnostics, I guess, at least in our sort of nomenclature. And they are really a large flood of data. They're just much more than the restart data, the stuff that you need for the initializing the model. Yeah. And so I don't know if you can thought to that, give them thought to that, because they're controlled in a completely model-centric way right now, at least for GEOS. And I imagine the same thing is true for other models. So how do you connect that to do you intend to put that stuff in R2D2 in the long run, or how do you make that connection?
Maybe both of us can.
Sure. Maybe.
I alluded to that a little bit, where there might be some issues and debate about making it interoperable and reusable. But I think the F and the A, the findable and the accessible, is starting to be addressed well with R2D2. Maybe you could give more comment on that.
Yeah. So over time, what we want to do is add like a greater search capability, new data types that we can store. The one thing about R2D2 is that you're not stuck with storing a certain type of data. And so we can, add new data types for storage very easily. We also store diagnostics as well. Maybe I'm missing something.
What I was alluding to is the fact that to write you're now to be efficient, the model would have to be calling R2D2 directly. And that isn't happening right now, right? I mean,
No. The EWalk workflow system.
Going to dump it into an NetSDF file, and some other process will have to then convert it and put it to a R2D2. And that's a very inefficient way of doing it. So
currently, one of the things we are looking at in the future, like we were talking about, maybe things like in memory, streaming data. So we are looking at how we can capture streaming data in R2D2, and also in the future, not just accessing just the files itself, but we're also, during this AOP, I'm working with Steve in order to implement like thinning algorithms, so different functions that could be applied to a data file before it leaves R2D2. We're also looking at including new data stores such as like HPSS. And so you'd be able to access data there as well. But right now with R2D2, those calls are kind of atomic calls that are made in individual tasks within the Skylab workflow.
Yeah, just fine. But let me just check something with Phil. So I see the last slot is 11:30 to 12. Is that actually a half-hour talk, or do we have some slack?
I don't think Francois was going to speak for half an hour, but so we do have some slack.
So because I'm happy to let this go because I think it's great to have this engagement on this. Are you guys good with that?
Yeah, we're good.
Great, thanks.
Yeah, I think R2D2 and Yoda are great things.
Oh, I wanted to make just one more point here. In this diagram, there's on the yellow level, there's a ... ellipses in that last box. So currently what we deal with right now is files and file storage, but that ... is there because the code is organized in a way where you can pretty easily add another way of transmitting data. So like maybe through a socket or through a RAM disk or something, and we can start using more efficient means of data storage and transfer and stuff like that, not so reliant on file I/O. I think that's a little bit of what you were getting at too, right? Yeah. Okay.
So yeah, I have one question about R2D2, so, and the data storage and the increasing volume and its curation.
Yes.
Really. by experience, I'm like work on chemical models. They have like tons of variable. And then when I'm able to cycle something, I'm producing a lot of garbage and I'm getting in trouble with like that. So, really, and this is what's going to happen at some point, So, what is the plan for curation? Do we have like a idea of how to implement this right now? Will you allow some users to remove some data? Right now, we cannot do that, I think. What is the...
Oh, sure. So we're going to be, we just started work. We just added new portions to R2D2 its API, so you can erase and delete, do that by indices or do that by keyword values. And of course, a lot of these functions that we're starting out with in R2D2 are really the kernel functions. And we'll be adding new functions that combine these kernel functions into, actual workflows that are within R2D2. So one of the ideas that we've had, I've been talking with Yannick about, is that we have like a cron tab or some kind of job that cleans out all of these experiments that build up over time that nobody uses, and clean those out automatically. But we'll also be introducing more tools on top of these kernel functions that allow users to change all that. We don't really track user information, but we do track what user created what experiment in Ewok, and then what data files are associated with that experiment. And so if you have the username and that unique experiment index, because we want to have an indexed registered system, it'll be easy for us here in the near future to start, curating that, because, we're going to end up having an exploding data storage volume that, really we only need like 20% of that's stored there, at times. And another thing to talk about with R2D2, we have two types of data stores. We have one called experiments that everybody uses to test with and develop. But then we have read-only data stores that only administrators such as Dom and I, the R2D2 system provides us administrators authentication to access and delete things. And then when we have like canonical data that we definitely want to keep, like Skylab 4 atmosphere land, we move that into a very protected bucket. And so it was kind of like we're sifting down over time into the final product that we want to present.
Thank you, Rick. So my question is about collaborative nature of this thing, because the development is in a collaborative fashion. So right now you have this database with tables, right? Mm-hmm. And say, a partner comes in and they want to capture a different set of metadata or different set of files. So if we go ahead and, add these capabilities, then every single user and deployment of, R2D2, and there'll be dozens, hundreds of those people, mm-hmm. will have to rebuild and port their databases. So, as a developer, it's like, oh, great, I want this feature, and it's your problems that, you need to rebuild your databases. But then the next day I'm a user and I have to keep rebuilding my database every time there's a PR. How do you imagine maintaining that cadence?
Oh, okay. This is a great question. One, we have a lot. We work with a Collaborate, like we said at the beginning of it. And one thing while I'm talking to, I wanted to thank Tarek Hamzy of the GMAO. He's an in-kind who's contributed dozens and dozens and dozens of hours over time of working on R2D2. So the way R2D2 is set up, it has basically two modes. You can set up the MySQL server and run it on your laptop and run small, low resolution Ewok runs on your laptop, or just run it locally. But then we have anytime you run any other simulation on an HPC or from an AWS parallel cluster, we have a controlled service that we maintain 24 hours a day. So we have one central MySQL server that's in the Amazon cloud that R2D2 always contacts and works with. And so in a collaborative, so there's no real database rebuilding. What we would do to add a new data type with new key values and new attributes is that we would work with the collaborators, decide what those are. And since R2D2's code is very agnostic, it's based on all the schema that's in the database tables, we would just add a new table into the database for your data. And then you would just start using the R2D2 code as normal.
I guess, but in your example, there is also 100 users that use a certain version of their own database, right?
Yeah.
So if they want to use a new version of RTD2, they'll have to rebuild their own databases. Because, their API will expect to have certain tables, and their local version doesn't have that.
What we provide is we provide the schema. So we do a versioning system of the schema for R2D2. And that schema is represented by an SQL file. And so we make it very easy to import that file. And then we want to provide tools that you would use to upgrade to the new tables. Suppose. Yeah.
Okay. Thanks, everybody, for that. Thanks really for this great engagement. This is such an important part of this whole endeavor, so we really appreciate that. Francois, thank you for your patience. So let's thank Eric and Steve. So our last talk of the meeting is Francois Hebert, and we're going to hear about non-local OBS operators in JEDI.
Good morning. So I was trying to find an excuse for a joke about having a longer slot, but we've solved that problem elegantly. So thanks.
Sorry.
So I'll be telling you today about a little bit of work that's been going on the JEDI algorithms team, expanding some of the capabilities of the system in terms of handling more sophisticated OBS operators. This has involved a lot of conversations with different partner agencies like NOAA EMC, GMAO, and the UK Met Office in particular. I want to point out the bulk of the development work here was done by Wojciech Szmigai, who was formerly at the UK Met Office, now a contractor with them. So let's dive right in. So I'll be essentially giving you an ad, right? So we have some new capability and I want to make sure you know about it, especially if you are thinking about OBS operators. On the title slide, I call this non-local. I think maybe a better phrase would have been OBS operators that probe a horizontally extended region of the domain. And I'll show what I mean by that. So after I give my ad, I'll also show an example application of the new infrastructure in the code to averaging surface fields over a field of view before passing them to CRTM. Many of you have probably seen a slide like this, but just as a recap to make sure we're all on the same page, when I want to compute an h of x in JEDI, I have to get the data from the model over to UFO, where the OBS operator lives. And so we've got a few different components illustrated here. The model interface repository knows all of the model details. It knows the state and the increment. It'll pass that field data over to OOPS. UFO has, some OBS operator. It is reading in a file that tells it about the observation. In particular, it'll know the coordinates of where the observations were. Those coordinates are passed to OOPS. In get values, we construct interpolation routines and we interpolate from the fields to the observation locations. We package all that into a data structure we call geovals and we send it back to UFO. If this is a little different from something you remember where the interpolation was happening all the way on the left, that's because we redesigned this a year ago. But this is what we have today. So the data being passed to UFO in this case is a column of model field data interpolated to the latitudes and longitudes of the observation, like this. So here's a case with not a ton of levels, just a cartoon for the sake of conversation. All the fields will be on this same column. So different fields may have different numbers of levels, but all the fields will be co-located on that column. And from here, you can do OBS operators like a vertical interpolation to some vertical coordinate of your choosing, or you can do some integral type computation along the column, maybe an optical depth or CRTM radiation transport. But we have other observation systems that are not super well modeled by a single vertical column. We have things like Doppler radars that look out or up, hundreds of kilometers. We have satellites looking down at an angle and probing quite an extended region on the surface of the Earth. And of course, the NSSRO taking long slices through the atmosphere. And, this is an opinion, but JEDI should be capable of handling all these well to be a leading edge data assimilation system. So we need ways of passing more sophisticated data to UFO. So this is where all the work is, but just in a simple summary slide, we have to really establish the requirements, which look like the ability to send much more generalized data from the model to UFO. So we're sort of thinking about this as 1D, 2D, or 3D slices, volumes of the fields. But in general, the data from the model does not necessarily live on the same node of the HPC system as the processor that will be doing the simulate OBS computation. So you really don't want to be sending completely unnecessary amounts of data around because that becomes very costly. So we want to think about ways of slicing all this, but be efficient in terms of the data. The little code structure cartoon I had before, I didn't say it in words, but it emphasized the separation of concerns where you have the model on one side and the OBS operator on the other side. And these things don't need to know about their own details, each other's details. And we want to maintain that. We want to make sure that to get these volumes of data moved around, the OBS operator shouldn't have to know anything about the model grid, and the model shouldn't have to know about details of the sensor. So the solution we've come up with, at least this first implementation, is we're going to sample slices of the model fields, n-dimensional slices with rays. So we're going to trace some rays through the volume and extract data along those rays. As a cartoon, we're going to keep building our cartoon here. So the blue column is what we had before, but say now we generalize this, we can support multiple different rays to represent one OBS. So like I said, many different samples, each sample being a ray. And we can also, as part of the effort to reduce the amount of data being passed around, we can select which field will be on each of these rays. So as a very questionable example, you could decide you want the pressure and temperature on the central ray and humidity on two of them and CO2 on all of these. Please don't do that. But this sort of flexibility is in the system. So this level is currently merged in JEDI. Things we want to do going forwards are slant paths, so we can handle these cartoons I was showing before of things looking sideways or at angles. We would be interested in tilting these rays each by sort of their own angle direction. So here's an example of what that might look like for a satellite looking down from above, or a radar system looking up from the ground. So, just to say it again, we can take these volumes I have defined before and sprinkle some rays through the volume to sample what the model data is doing there and extract this data to send it back to UFO. So let's talk about the code structure again. So now things got a little bit more complicated, right? So the locations method of UFO, of the OBS operator in UFO, used to just tell you two numbers, a latitude and a longitude. Now it is also responsible for deciding how you're going to sample the relevant volume of space that you want to use to model the observation. In other words, it has to select which rays you're going to trace from the previous cartoon. The data being passed to get values in OOPS is now a little more complicated. It's not just a vector of latitudes and a vector of longitudes. It's a map from variables to sets of rays. So you would say, for pressure, I want these rays, and for temperature, I want those rays. You now, of course, have to do more interpolations, right? You're asking for more data. So this is a little bit the cost. You're going to get more data because you've done more work. The GeoVals now has more data coming back towards UFO. And it is the responsibility of Simulate OBS now to work with this extra volume of data, and it will hopefully know the sensor details and combine this data appropriately to model your observation. What does this mean for you? If you are still doing, if you're not trying to write an operator with this extended domain of sensitivity, nothing changes because the interfaces are preserved to have the same current behavior if you use the current interface. So this can be completely transparent. If you do want to do, a new radar operator or something like this, you're going to have to think a little bit about what is the cone, what is the beam pattern, how do I want to sample it, what is the most efficient way of doing that. And the OBS operator will be responsible for generating the sampling and then computing h of x from those samples. So I've given a very cartoon level sketch of this new infrastructure. If you work with GNSSRO, you'll note I completely glossed over the fact that we already do have an operator that is 2D in the sense that it can work with a 2D slice through the atmosphere. This was previously done in sort of a hacky way where it was just a vector of 1D OBS, and now we've formalized this inside this new infrastructure, so the infrastructure is in use. So what I want to talk about next is a new application to this field of view averaging of CRTM surface fields. So what does that even mean? The CRTM is used to simulate satellite observed radiances. And this takes in as input data from the surface where we have reflections and emission, as well as the radiation transport through the atmosphere where you have scattering, emission, absorption. So the geometry is in that left little cartoon there. You have some cone looking down. It sees some ellipse on the ground. But the way we are currently modeling this in JEDI, and in fact, as far as I know, EMC as well, is we just take a vertical column at the center of the cone and you determine some unique set of values for the ground at that location. What EMC is doing and what they've asked us to replicate for their validation is averaging the surface fields over the ellipse, which is a good way of capturing some of the variability inside the field of view. You expect the surface may change more dramatically over an ellipse than the atmospheric fields, which are going to be smoother in general. Oh. Okay, it is laggy. Okay, so the way this is done in the GSI on the left is you compute what that ellipse is that the satellite sees because you know where it is and you know the angle of the sensitivity, the field of view. You know in GSI what the GSI grid points are. So you just count the number of grid points in there. You use those to sample, say, the surface temperature, and you average over this region using the antenna power that you know for your sensor. Typically, this could be hundreds of grid points inside that ellipse. What JEDI is doing today that we're trying to improve on is it just interpolates to the center of the footprint, so you completely miss any variability across the region. What we're testing using the new infrastructure is dropping a whole set of extra samples of the surface variables throughout the ellipse to go along with the upper air sampling in the center. So this is taking advantage of that feature I described where we can select which fields go on which rays. I've been testing using a very naive uniform grid with a few tens of rays, and there's a lot of room, well, some room for improving this. The data volume, of course, doesn't look like this because all these orange things are surface fields. So the data volume looks like this. It's surface fields on the samples in the ellipse and a column in the middle, which is a lot like GSI. The main difference, of course, is that the stencil in GSI is set by the grid. In the JEDI application, we don't want to have that dependence. So the stencil was set by the OBS operator. In the test case, it's very naive. Long term, we want something that is actually, collecting the resolution of the sampling to where you're most sensitive. And then you average using the antenna power. So I'm going to show just a few initial test plots of this on some AMSU-A data. So of course, this is not the data. This is just the locations of the AMSU-A OBS for now. And I'm showing you the input to the CRTM for the land area fraction variable. So upper left is GSI. You can see, land is land, and land fraction goes to 0 over the ocean, and the northern latitudes where you have a lot of ice and snow at this season. The lower left panel is the difference between JEDI today and that GSI plot. And you can see significant differences along coastlines and in mountainous regions and sort of the edge of the snowpack. And this is where if you have I'm not sure how well you can see it from the room, but there's sort of greenish dots in the GSI data up above. These are regions where over here you see, 50% land, 50% snow, for example. And JEDI today is just picking out, it's one or the other depending on what's in the center. If I turn on the averaging over these little footprints, you see excellent agreement with what GSI is passing to the CRTM. Here's a very crude initial test of using that into an HFX calculation. Here, the agreement is not as good because I have not done all the hard work of, making these things match. And this plot is a little bit old. So there's some things that we already know. I think I've missed some of the cloud microphysics, as Greg was telling us 2 days ago about some improvements there. There's a bug in the vegetation fraction units that is showing up over Australia. But you can still see, even though there's these things that need to be validated and improved, you can see clear improvements where JEDI with FOV is a better match to GSI HFX over coastlines, over the Great Lakes of North America, over the mountains in Western China and different areas like this. So on that project, next steps are to do that properly. So I'm going to be working with AMC to do the validation more carefully. It's probably worth spending a little bit of time sampling the field of view where the antenna power is highest instead of just uniformly. And then, getting all this merged, because the underlying framework is merged. This is just now using it. And the main takeaway that I want you to have from all this is, we have this new infrastructure that supports non-local OBS operators or that are sensitive to broad regions. The next steps for me are going to be worrying about this slant path problem, but also hopefully talking with you about your new operators. If any of you are interested in developing something that we can now support, then hopefully this has at least alerted you to the possibilities, and feel free to talk to me or the JEDI team about how we can make it work. Thank you.
Any questions? Please.
Nowadays,
You can tilt that down if you want.
Okay. So there are drone observations a lot nowadays. It would have a different observations at different location, X, Y, Z, and T. How do you see, to make it HFX efficient for that kind of observations? I mean, especially in the local observation.
Yeah.
How do you see, to deal with that kind of drone observations?
So are you worried about the amount of interpolation that has to be done, or
how to use the data? For example, we have a glide observations produce a temperature salinity twice a day, within a 13 kilometer. Okay. So it has an X temperature salinity, X, Y, Z, time variant from the one observations. So now I want to use it. Currently, what we are using it just collapsed in one profile at one time. But I like to use that information at the different time at the different depth.
I don't have a clear answer for you right now without having looked at the details. I don't know if anyone knows OBS questions better and wants to chime in, but I mean, that sounds like a good concern, but I don't have.
Maybe I can.
I guess I don't understand how it's fundamentally different than what you're dealing with, but that's probably because I don't understand enough.
Yes.
But wait, please.
Yeah, I try to see whether I comment on the point. I think right now what this part, the GeoWire part, it actually deals with the geographic interpolation. So it X, Y. And you are talking about the time, temporal one. And there's a way, one is that you deal with UFO as a single observation, then you can have different time, or your time window, or 4D-VAR, 3D-VAR, right? That's temporal part is not handled by this part. So I think that's your question.
Thank you.
Yeah, good work. Not challenge. Just a quick comment. For the M3, the nadir, you look down, and you look side, the surface area difference. And also you have to consider scan angle as slant path. That's at the moment we use as angle correction, that's we consider that. Another thing is probably you need to consider for different frequencies, the effective fields of view is different. So for the GMI, the 10 gigahertz and the 89 gigahertz, the effective area is quite different. So you have to about that. I'm not sure because that stage. Anyway,
okay, yeah, so that's it. Yeah, thank you for the comment. So for the slant angle, yeah, I mean, that's, as I said, that's the next step. And for each different observation, we can set all the rays as we want. I don't think we've treated so far at any part of this pipeline the frequency of the obs as being sort of a variable, a knob. So in the current infrastructure, we would have to do the same sampling for which could potentially be improved on, but it sounds like, unless I suppose if we were to split it as different obs, but now I'm just.
So basically the lower frequency would be the biggest volume.
Yes.
And then as you go higher in frequency, like you were showing, you'd be excluding more and more points because it actually constricts. It's just diffraction limited based on the frequency.
Yeah, so either you need a little bit more code than we have now to optimize for that handling, or you sample to handle all cases, and then you have maybe more data being passed around than you need because you've oversampled the broad footprint and you've sampled outside the narrow one.
I have another solution I can talk to you about, Genju. Because I would actually just treat, it's really trivial to take a sensor and treat it as 5 sensors.
Exactly.
I would split it up and make an approximation and say, these sets of channels, you do one averaging, these set, you do another set, these you do another. So you just, in your YAML, you just do the same sensor, but you have it in there 5 times. And then you can treat them all a little differently.
Any other questions?
I have a question online, Ron.
Oh, thank you. Isaac, is that you?
Yes, it's me, Isaac. Yeah, thank you. So this is really interesting. I have 2 questions. So not only it's important to sample the profiles, it's also really important to first pass the profiles through CRTM and then average H of X based on the antenna pattern. So I don't know if that's what you're doing or not. And then my second question, then you can answer it, is it would be really nice to have something similar to average observations because, for example, for a spaceborne radar for CloudSat, let's say we have a resolution of a few hundred meters for the observations. So we actually need to average our observations to match the model grid. And as long as I know that's not possible within JEDI, so you have to do it really offline.
So to the first question, I will say that I agree with you, and that is something that we can quite easily do with this infrastructure. To the second question, this is outside my expertise.
And it doesn't look like you're getting any help.
Yeah, it means it's not there.
What's that, Isaac?
So I mean, it means it's not really there in JEDI yet to do like a spatial or vertical averaging for radar observations.
You're talking across different observations?
No. So for when the observation resolution is higher than the model resolution, you have to do super obbing your observations. Anyway, thank you.
Thanks, guys. Guillaume, were you going to make one last comment?
I'm just going to try to maybe rephrase the question from Hansuk. Maybe I understand it, but maybe not. So I think he was talking about gliders, which you have the exact position at the time the glider sinks and goes wherever, and then you have an uncertainty of like a cone of uncertainty of where the glider is going to be, and then it pops up somewhere. And I guess the question was, can you have a ray that would kind of sample, but it would be in time, right? Because it goes down, it goes somewhere that you have some fairly large uncertainty of what is actually being sampled, and then it pops up. And which means that your rays would have to be time independent in that case. And that wasn't the question.
Okay, I don't know if I want to answer this off the cuff. It seems like that's not like at each, if you can make a guess for where you're trying to sample at each time, then you would just sample it the way you do any other obs at that time. And the fact that basically the uncertainty in the location is the same as a broad, domain of sensitivity. That's one way of thinking about it, maybe, but maybe there's a better answer. I see Yannick is walking towards the microphone.
Is it working? Yeah.
Yes.
Yeah, it's the responsibility of the ops operator to do that. So when you query your ops operator to know the location, that's called at every time step or a certain time resolution. So you would have, it's your ops operator that would have to do that. You give it for each time over your area of that you want to sample, and the code that Francois developed will give you that. And then it's your ops operator that has to do something with it, which is up to you.
So, wait, are we about to, go.
Okay, I want to make a comment also related to the previous question, because we need to remember what Francois is talking about is our model space. And that's what the interpolation, etc. happen. And related to what Yannick just mentioned, there's also something happening over observation space, including super orbing, etc. that can happen over UFO side. So we need to distinguish these two parts because, for example, the temporal, etc. can handle all the observation space. And it's just two different domain over there.
Thank you, Hui.
Okay. First, let's thank Francois for a great talk. Then let's thank all the speakers actually throughout. That was really great. I'm assuming you're going to want to make some comments, but before you do, can I say a word or two before I give up the microphone? So I just want to talk about this session first and the meeting as a whole. A lot of, I'm going to generalize a little bit, but, we saw this very slick demo yesterday. And a lot of things are just happening after you click buttons. And, a lot of what we saw this morning speaks to the incredible thought that goes into sort of making that kind of a turnkey thing. So it's really, really impressive. So this is really slick. The amount of thought and expertise that the Joint Centers put into this stuff is astounding. I would just say something, take advantage of my seniority here. I've been involved with the Joint Center a long time. And since we last met in 2019 in person, I guess it was maybe in NASA headquarters in DC, the evolution of things is tremendous, honestly, not just the Joint Center stuff, but I think what the partners, the progress and the investment the partners have made and how far along they've come. Both of those things together tell me we're on the right path, right? Neither of those, let alone both of them, would have evolved so. So I think that's really fantastic. So congratulations to everybody. And this truly was a workshop, in my view, in the sense of it wasn't just dog and pony. There was a tremendous amount of engagement. So I certainly don't feel bad that the government spent money to send me here this week. So that's great. So thank you very much.
Thank you, Ron. Okay, well, thanks Thanks for your comments. Thanks for sharing this this session, and especially you managed to board your plane at the same time. Yeah, that's it. So yeah. So we've reached the end of this workshop, and we're going to have a wrap-up session now. It's been a fantastic experience. I'll definitely echo everything that Ron just said. So in a few minutes, I'll ask you to take your thinking hat and come up with your thoughts about the workshop. What resonated with you? What's your take-home message from this workshop? And also, providing us some feedback. How we can improve the next time? Because we really want to use every feedback to come up with even better workshop next time. I can't believe last time we had in person was 2019, so 4 years ago. Yeah, how could we survive without this, influx of jointness? And this is fantastic. Before we go into that session, I really want to spend a few minutes on thanking everything that happened in the background to make it such a smooth event. And there's a lot that happened actually in the background, in terms of registration, the webpage, the organizing, the catering, the IT. It's non-trivial to have a virtual event with remote attendance, remote presenters, and screens and posters and everything. And in my mind, it's just we've been taken care of fantastically here. So this has been extremely smooth. And the smoother it is, the more preparation it requires in the background. So I'd like to invite Phil, who's been instrumental in all of this. You've been at the center of everything. I didn't do anything. He basically did it all, and he's been in the center of a team. And I'd like to invite you, and please join me.
Well, thanks to you. Thanks, Tom, for those words. But I just want to actually say thank you to you all. I think this event has only been a success because of your participation. So thank you to all of you who made the trip out here for the fantastic talks, the posters, all the presentations throughout this week. I always tease the guys in the team that I'm not technical at all, but I've learned so much over the last couple of years. My first one was in 2019. And I actually said to a few people this week, it would be fun to go back and actually have a look at all the presentations from 2019 compared to now to see actually what we've done. We've evolved into an application, which you saw yesterday is pretty fantastic. So yeah, just thank you to all of you online as well. It's always tough attending these things online. We tried to do a virtual event a few years ago. So happy that we can actually come together in the room. We look forward to doing this again next year. We're going to start talking about who's going to host that and who's going to volunteer the facilities for that. So I guess watch this space. As Tom also said, behind the scenes, there's always so much work, and I'm not sure if they can hear me, but we've had so much fantastic help from different programs within UCAR, the catering. Sylvia Ng has organized that, so thanks to her and her team. Shelly Rayburn, who's been sitting at reception the whole week. Thanks to you, Shelly, for all your fantastic work. And Kelvin, is he back there? Kelvin, thank you so much to you and your team for keeping us going throughout the week, dealing with the technical difficulties. And we know it's always tough. So really, it's just a group effort. So thank you so much to all of that. I don't want to steal everything that Jim's going to be talking about, but just one other thing. A lot of you have asked me about presentations. What we're going to do is give us a little bit of time. We're going to compile the agenda with links to all of the presentations that you've seen this week, as well as digital copies of the posters. And then, of course, we have the Skylab presentation that will come out in the recording as well. So there's a whole bunch that you'll get to refer back to over a period of time. We in the process of revamping all of them, the multimedia side of JCSJ on the website, and also so watch this space. We'll be sending out a lot of info on that. A lot of you have said to me, "Oh, you're the guy that sends out all the emails." So look forward to more communication from me in time to come. So it's great to have met you all, and thanks again for being part of this successful event. I'll hand over to you.
Jim is going to run that last session and really invite you to speak to this. Let me start with giving you my quick thoughts and sort of leaning on this analogy of the concept car that's been used extensively in various domains. A few years ago we were building pieces and components, and now we're really assembling all of these and seeing really a massive amount of value of this. And we have actually all the partner agencies really keen on actually transferring this into operations, really building these production cars out of that. So on Monday before the workshop, we had actually a meeting with our management, our oversight board, where we have actually all the partners coming in and saying, this is a fantastic, demonstration of collaboration. We're all in, and we're really keen on making this work. So I just want to make also say I'm really grateful for the commitments from the agencies. Nothing would have happened without actually that big leap of faith, and we're actually in this because of that. So that this is great. Continuing on that concept car, I think what's important also is not seeing just the shiny things and new features. There's like a flashy paint and fancy wheels on the new car. It's also all the infrastructure that we're building to actually being future oriented, making that scale, making that actually work. Having that collective intelligence where we have actually a lot of folks from different teams from different backgrounds coming in, and we managed to speak the same language. We actually managed to bring all that together. So this is actually really cool. And we have actually these world-class science components that are coming in. So fancy features. I start seeing wings being developed. So we'll have a flying car in the future. Really, that's where we're heading to. So with that, I'll pass the mic and stop, talking about concept cars and and invite you to come in with your thoughts.
Thank you, Tom. So, I had a lot of questions and all written or things to say. Unfortunately, the questions for you guys remain. So I'm sitting here, well, Ron's stealing some of my thunder, and then Tom's stealing a little bit, so I could just sit down. But I think there's a really important point that with the first workshop in 4 years, there's a lot of pent-up demand that we can kind of feel that being met. But before we engage in an end of camp, summer camp, group hug, feeling good about that, let's look objectively as we can from what we got out of the workshop. And by that I mean we as all the individuals. What worked for you, what didn't work for you, what was missing, maybe who was missing for this particular workshop, and what you'd like to see when we do this again in a year. And just one other thing I'd throw out there is just to be thinking about kind of the one thing we have been able to do through the pandemic is we've been able to have our symposium every year at the AMS, and I just encourage everyone to take part in that in Baltimore next year. Call for papers will be coming out soon. I anticipate we'll have like this every year, a full day of oral presentations, which means 22 slots and posters. And I think getting our whole community, this group there, but engaging with the larger community is really important for us. So that's just something to keep on in mind as we come along here. But I really would invite people to come to the microphone, and I'd like to hear voices besides the old stalwarts. Ron, Ricardo, me, and I mean really what I'm looking for is for people who have not been engaged and coming to these meetings as long as some of the names I just mentioned have, to say what worked for you, what you'd like to see more of. Maybe if there's something didn't work for you and it was a waste of time, let us know that. So I'm going to open it up. Young people are way too shy. Oh, okay. Peter Jan is at least 3 years younger than I am, so that's good.
35 years in data simulation. I've been very frustrated with not being able to work with the real stuff. Yeah, it's easier, I guess. Not being able to work with the real stuff. I try to work with the Met Office system, and if you talk to the Met Office people, they'll tell you, okay, this is not gonna. The system is just too difficult. No one understands the system anyway, and you can't do the stuff, the kind of things that you want to do. And I think here we have something that's great for academia to be fully involved in every aspect of data simulation, and even the operational stuff. So it's absolutely fantastic, and I think this workshop was fantastic for me to learn and what's out there, and the Skylab is absolutely crazy in that sense. And we need to draw in more academics, and we will. The big thing that is needed, and I said it to all the agencies, we need to train the workforce. Now we have the tools to actually do it. So if you have students, right, I mean, they start now working with JEDI, it'll take 3 to 4 to 5 years before you can actually use them. So we need to train those students now. I've said it to many people, and I really think we should do this in the US to push this whole thing. Okay, I guess I stopped there. Oh, and the other thing is, so I know all the agencies deep in their heart, they think, okay, ECMWF, all those years, it was always ECMWF. We'll beat them, right? I mean, this is going to be the way. And unless ECMWF joins, it will be great, and then we have one big family. Thank you.
Okay, so thank you, Peter Jan. Who else has thoughts on, again, what worked for you? Was the format work for you? Would you like to see more talks, more open discussions, more time for posters? Less talks, less posters? I personally would want to say, again, that some of this is what happens over 4 years and not being on site is, a lot of core staff have been hired, so it's really gratifying for me to get to know some of you face to face. There's a number of you I've written or I've paraphrased your biographies for the newsletter, but it's really gratifying to come and find out. For example, there's one person besides me in the Joint Center who speaks without an accent. I appreciate that, Eric. It's so no, I mean, good. It's gratifying. So yeah, it's from south of the Mason-Dixon line, I'm thinking. But on the other hand, and this is just, I didn't feel like I actually did the time to talk and get to know everyone on the core staff, and and even know what they were doing until some of you got up and started making presentations this morning. So, oh, okay, that's who does Vader, and so I could have used some more time. I think that was just for informal conversation, notwithstanding that we didn't have a fair bit of it. Maybe one mass enforced merriment event, out somewhere. I do not wish to dominate this conversation. Wait, thank you. Get the mic right.
I'm not that young either, sorry, but as a June Center person, I want to say first, I feel very beneficial, even though we talk with our people, frequently, but it's always good to hear with a bigger, clear picture through the presentations. And I feel I learned a lot, even just from some content I have heard before already. So I feel this time is really a science workshop, but also a technical review. I feel we really did a good job to go through that direction. So I feel myself, I benefit a lot from there. And of course, I also appreciate, yesterday I actually told Nancy about that too. I feel very beneficial to me to hear from our partners, their view and their timeline, because we are doing small scale work, putting one sensor in or testing QC, etc. But actually knowing that, or our partner agencies, actually those things putting together, and one day it become a real application. I think we know the big picture. They help us to know where we are and what we are missing. I think that kind of feedback usually doesn't happen during the quarterly review because it's more quarterly talk. But now we actually have a big picture through the different time scales, and we actually knowing what we are doing and how we can interact with each other better. I think that's very nice.
So I've only been with the Joint Center for 2 years, and there's several of us in the core staff that's only been with only a few months. And so a lot of us do not have atmospheric science backgrounds. Like for me, I'm nuclear astrophysics, for example. And so before I started working with the JCSDA, I'd never even seen any atmospheric science. So the cool thing about this workshop is not only to learn more of that on the technical side, but there are so many different components that are working together within Skylab that we're in JCSDA that we're developing. For example, like Steve's talk on Vader. Like I kind of had an idea of what Vader did, but I had no idea about, how the algorithms work, the recipes, the cookbooks. And I think a great thing about this workshop is people who have the different backgrounds to, learn about the science and learn about the technology of the different components that we work with every day.
Appreciate that, Eric. Michael.
I thought you guys did a really good job of showing both science and the technical aspects of JEDI, and also as someone who's been at university for a long time, it was great to hear updates from all the operational centers, and as well as kind of the technical aspects of what they're doing as well. So that mix of kind of software and technical and science presentations was really just about right, I thought.
Yeah, you make an interesting point. We mentioned, someone said if you looked at the presentations from 4 years ago and compare them to the ones made this week, and I think you were probably talking about what I would call the science technical specific ones. But actually, it's also interesting to see again how the agency engagement and the clarity of ways forward have evolved in 4 years too. That's getting both parts of that. I was glad to see that the executive team members, by and large, were able to stay here throughout the week. If I could have done something different, and I'm not sure how we could have done this, I would like to have had the demo run for as many of the management oversight board members as possible while they were here. That was one thing At the same time, I think, well, okay, without the underpinning science, as you mentioned, seeing the level of thought going on underneath the demo was important as well. There's no perfect way to do this, but consider the pros and cons. Please.
I want to put some of the people in my own organization in the spot a little bit. So, we brought a bunch of people here who are either young and or, maybe don't go to meetings that often, and they contribute. Oftentimes you go to a meeting and there's this sort of, the people have been around forever. And, and then for the younger people, it's sort of harder to engage and feel like everything's accessible to them. So I would really appreciate your thoughts. I guess I'm staring at you because I don't know. What I've learned over the last several years, we've hired a bunch of great young people, and it's been sort of such a shot in the arm for me to sort of be enthusiastic. And unfortunately, it's going to make me stick around longer. So, you shot yourselves in the foot. But what can we do, or what hasn't been done? What didn't we do well enough in this meeting to sort of, do you feel it's open enough to you, accessible? Is there anything, about the process that, was hard to engage? Is the point of entry, accessible enough to just sort of jump right in and be part of this? Are there ways in which we've done this, made choices in the way the meeting was run or how things got selected that could have been improved to just integrate quickly? Is there anything on the top of your mind? If not, you can tell me afterward, but please be critical. Looking over here too. Oh, because I was about to say we were perfect.
Well, I have a software engineering background, and basically all of this went over my head, except for today. Today, I pretty much got most of it. I still don't know what B means, and I've been sitting here the past like 2.5 days. Okay, great. But I also understand that I might not be the target audience for this talk, so I don't feel like complaining about it too much. But yeah, that's just my thoughts.
I mean, that's an important point. And I think, how there has to, nobody can be expert in everything, but, and I'm definitely not a software engineer. I used to write some nice, structured Fortran back in the day for research purposes, but that's about where it ended. I'm not I'm not a modeler or data assimilation specialist. I'm really an instrument person. So physics really when it comes back. So yeah, I think you make a good point, and that some of the material is always going to speak to you more than others. I'm hoping that, that having our whole community together, though, we start to get, the big picture pieces, because, yeah, I mean, some of us have done the science for 30 years without recognizing that really to make the progress we need to make, we need to get past being what we thought of as writing our good code, to having, actual software engineering practice so we could make advances in our software that keep pace with the advances in our science.
So I'm coming from the coupled hurricane ocean modeling system development team, and before I come to this workshop, I asked. I asked the data simulation people for atmospheric side. So they have been using, GSI based or, different types of data tools, data simulation tools they've been using it. But these three groups that I know got funded to convert the GSI based data simulation into the JEDI frame. So the first thing they got lost is that there's no point of contact. If they want to start to convert the GSI based data simulation into the JEDI, they don't know where to get the help. Okay. So, there is no sort of support, for, what I can say, in a team or something. So they give them a guidance, step by step how to do it, that part. And the second part is there's, coming from the university side, all the JEDA, code is based on C++. Undergraduate and the graduate students are not quite familiar with the C++, not talking about the Fortrans. So, so sort of education, obviously it's a part of the university policy, but C++, so object-oriented program, it's still lack of, lacks in the, university curriculum. But, to start off, how are you going to help people? The points there.
Two good ones. I mean, like you say, there are people who are, I guess, woolly mammoths in their programming. Then there are those of us who are dinosaurs. So I'll go to Anil. Oh, I'm only figuratively standing between people and lunch, not literally, so I feel fairly safe. So if you've got a question, you'll be the one in danger.
I felt I needed to speak for the young people in the room because that was a joke. I'm not young.
I know.
Thank you. And, to reference your question, I have a PhD in numerical weather prediction, and a lot of this went over my head. because I've been in management for too long. And that goes to my second point, or my main point, which is from an organization, as a mob member from an organization like the Air Force, this is extremely beneficial for people like me, because we don't have an overabundance of people in this room, as you can tell, who do the science. So to be able to get back and convey and help convey all of the advances that are being done really just helps my job. And I really appreciate all of the discussions specific to this. It's my first time to get one of these in person, and it's really beneficial. And maybe, I don't know if it'll help some of the younger people that are coming in here, but maybe at the beginning of the meeting, can have like one slide that kind of outlines the organization of the Joint Center. I mean,
yeah, that's a good point. I've been to so many meetings where we did that. I guess it's like lost in my back, but you're right.
And this is not to put more pressure on the Joint Center at all. Some of you are familiar with, the adjoint workshop that Ron Errico used to run. And at the beginning of the workshop, he'd give this lecture, or there was time set aside at the beginning, and he'd give this talk, what is an adjoint? And we made fun of my good friend Ron after 20 years of this because it was the same 10 slides. But it was really a very nice, intro into the terminology, the frame, just the sort of the basic concepts. And I don't know whether that's, what the right forum for having that sort of a little primer is, whether it be before this or, we have the summer school, there are lots of things, but they're targeted for different things. And I'm not even sure it's the Joint Center's responsibility, but I know Ron made a point of, that kind of fundamental thing about the concepts about what we were talking about. I don't know if that could some sort of what's be worked into this or along the lines of that, but it would be part of the outreach, I suppose. Anyway, food for thought, not do it, but because it is a good point. I mean, in some sense you have to learn. So, you know what I mean? That's part of doing this. But in the other sense, if there was something that could be done, maybe that'd be nice.
And with the word, Curtis.
I guess just sitting back and absorbing the last 2.5 days, first time in person for one of these as a representative here for NOAA. And I think the Skylab demonstration yesterday afternoon was particularly impressive. I found that to be a really instructive demonstration. And I want to think about in future science meetings, perhaps expanding that to having an opportunity for other partner agencies or collaborators demonstrate some of the application-specific work that they're doing. Obviously, Skylab's going to mature, can add on to those demonstrations. So think about it as another dimension of presentations beyond the PowerPoints and the posters to another way in which we can look at some of the work being done. So I just thought that was a really effective tool yesterday and would like to see more of that in the future.
Yeah, and from my point of view, posters are always more effective than PowerPoint. And I'm going to go to Victor.
So I'm most new and young, so I'd like to
enjoy it.
I'd like to join Akira's and Ron's point of view. I'm not from atmospherical background either, and sometimes it would be nice to come from have a small presentation at the beginning of each day about for people that are obviously that don't know about these things. I'd say maybe in a few years, in a few GCSA workshop, I won't need them, but.
So maybe like a session intro talk, what's motivating this? Okay.
Kind of, yeah, maybe only for the young or for the new one, maybe, or something.
Or to get us on the same page. So for all of us in that sense. Ricardo.
Okay, I wasn't supposed to talk because I'm old, but the old have talked. So
not as old as I am.
No, I was just gonna say that. I mean, I have no words that can convey how great I think this was. But if there could be the little bit more time, or some slots could be devoted to just open slots where people can then sit down and discuss. Maybe we can benefit. Maybe, like for example, today we're ending in the middle of the day, so it would have been perhaps plausible to have had like yesterday afternoons, for example, open. So it would end of the day today, but then we would have had time to have sort of, separate discussions and things. Because we end up having those, but a lot of times like at the posters and stuff, but perhaps not enough. So something just.
Okay, thank you. Doruk?
Hi, everyone. I'm Doruk. I work at GMO with Dan Holdaway and Ron. And I wanted to say, I started my job last September, but the GI system I find it really amazing. But it was kind of straightforward for me to adapt to the system, and now I'm cycling. It shows like the amount of effort that's put into it. It's like really great, and it's at a stage that I personally didn't have to use any. I did more software engineering side, so I'm doing more Python coding right now, not like Fortran. But it's in terms of adaptability for someone who is not familiar with the system. Quick. I just wanted to make that comment. So that shows. It's probably I have advantage of working with Dan Holdaway, so yeah. He answered the question I had. That's one comment I wanted to make on Jedi. In terms of the meeting format, so the size of attendee, like it's 100 people. Compare that to AG, like thousands of people. I always felt really overwhelmed with the AG session. There's like rows and rows of thousands of exaggerating, but you just don't get that personal interaction, and you don't retain any information. But here, like I saw a lot of overlapping work, the cycling, Skylab, eSQL. So that was really nice. And coffee break, I'm able to, of course, but it feels smaller and more intimate.
Okay, other questions, comments? And seeing none, I will thank you. Oh, here we go.
I attended this workshop for 10 years now, since the first time, 2012. This is now after pandemic. It's good to see old friends, make new friends, and I work on Jedi, I work on Jews, and got lots of questions and ask people. I appreciate the Joint Center's staff. Wow, help me. At the beginning, it always lots of questions. I have no idea I have no C++ experience at all at the beginning. So it's good to see all of you, and I thank you for the help, and I appreciate, and I believe there'll be big progress next year. This time. That's all for me.
Thank you, Jay. All right, I think we should close the meeting and get to lunch, and everyone have a safe trip home if you're traveling.